Hi, my dear NEET warriors. This is your Captain Shreyas on the Vedantu NEET English channel. Welcome aboard. Do let me know if I'm audible and visible. Hello, Shri. Hello, Meghna. Hello, Hey Malata. Hello, Sony. Good afternoon. Good afternoon, honey. Good afternoon, Crazy Girl Nanny. Banot, Perfect Things. Welcome, Meena. Welcome, everyone. Yes, I hope I am visible and audible to all of you. Very good. Very good. Very good. So, my dear students, what have we assembled here for? We have assembled here for, the graphs, the complete graphs in one shot for your NEET 2024 physics. So, we are going to see all the important graphs, and also at the start, I am going to teach you some basic things which you should know regarding any graph. So, for the entire physics, even for chemistry, you will need that basic theory of graph, and then quickly we will go on to all the graphs for all the chapters 11th and 12th standard, right? So that is the aim of today's session. So thank you for joining in, and quickly smash the like button for your Captain Shreyas Sir. Yes, your physics master teacher, and nice to see you on this side again. Yesterday we were in the Chennai Vedantu Learning Center, Anna Nagar, and we had a lovely workshop with all the lovely warriors. What a wonderful event it was, and thank you for turning out in such large numbers and showing your immense love, and I'm pretty sure you have benefited a lot from yesterday's workshop. And today we have the mock test which is running absolutely free of cost, and a lot of students are already giving it. Thank you. Very good. Good afternoon, Krishna Sakti. Hello, Ili, Fiza, Divya. Nice to see Gujarat, Fiza, Abhinya, Vishal, Hanipriya. Hello, Serena. Good afternoon. So let's begin with the session, my dear students. Yes, you have liked the session. Very good. If you like the session, very good. And if you have not yet subscribed to the channel, or else you will miss all the videos. Okay. So all the warrior pointers, get ready. And also remember, in the description box, there is a link for the mock test series, which is absolutely free of cost. So utilize it. All the resources are meant only for you. So utilize it. These mock tests are newly made mock tests for the updated pattern based on what NTA might do in this particular year. So use this. You can give it offline or online at the exact same time where your NEET is, and there are 6 to 8 mock tests available free of cost for you. If you want to give it offline, you can give it in many of the cities at Vedantu Learning Centers. If you want to get the proper experience of the pen and paper, bubbling, OMR sheet and all of that. But if you cannot travel, no issues. You can give it online also. You will get report cards, solutions, ranking, everything. Okay. So where is the link? In the description box. Right. So let's start. Let's start with some basic graph theory. So starting off with, let's say, if I talk about, certain important graphs which you should be very well aware of. Number one is, linear equation versus straight line equation versus cubic equation. See, when I write y is equal to mx plus c, what it means is the graph is going to be a straight line. It is going to be a straight line, and the graph is going to intersect the y-axis at a distance c from the origin, and the slope of the graph, that is nothing but your dy by dx, rate of change of y with respect to x, is nothing but m, and this is going to be a straight line. What is it going to be? It is going to be a straight line. In this case, you can say that the slope is positive. In this case, the slope is positive slope, and maybe if the graph goes like this down, then I can say that it has got a negative slope. It is going downwards. And if by chance the graph went like this, then I would say that the slope is nothing but 0. The slope is nothing but 0. It is neither going up nor going down. It is a constant graph. Yes, in such a case, y will be just a constant value. It is not changing at all. Next thing up is if the graph is a quadratic equation. If the graph is basically a quadratic equation, imagine something like this. Y is something ax square plus bx plus c. Now there are many variations in this. There are many variations in this. Understand. Example, y is, imagine it is 2x square plus 3x, okay, 2x square plus something bx plus c. Do you see this number 2 is basically positive? This number 2 is basically a positive number. So the moment it is a positive number, you will see that the graph will be a curve and it will be an upward parabola. It will be an upward parabola. It will be an upward parabola. It is no longer a straight line. It is an upward parabola. But at the same time, if instead of 2, let's say it was minus 3, some negative number, some kind of negative number. So y is equal to minus 3x square plus bx plus c, then you will see that the graph will be a downward parabola. It will be basically a downward parabola. It will be a downward parabola. Very, very important thing which you should know. So the coefficient of the square term, if it is positive, it is upward. If the coefficient of the square term, if it is negative, it is a downward parabola. So what matters over here is this number, A, right? Similarly, the next thing which also matters is this number C. For example, y is equal to some ax square plus bx. Nothing else is there. Okay, nothing else is there. Imagine it is just 0 plus 0. Then you will see that the graph will pass through the origin. If by chance it is y is equal to ax square plus bx plus, let's say it is some positive number, let's say plus 4 or something like that. So 1, 2, 3, 4, maybe 4 units up, the graph will start from plus 4. The graph will start from basically plus 4. If at the same time, if it is not plus 4, let's say it is minus 2. Example, if it is minus 2. So y is equal to ax square plus bx minus 2. Then you will see that the graph will start from minus 2 like this. So this point will be minus 2. Right? So this constant c decides where does the graph start from. The constant c decides where does the graph particularly starts from. Agree everybody with me on this? Very nice. Next important thing which you should know is whether the discriminant is positive or negative. That is the discriminant, which is b square minus 4ac, which is there. There are three possibilities in this. One is the discriminant is 0. The second possibility is the discriminant is basically more than 0. That means it is positive. And the third possibility is the discriminant is less than 0. Accordingly, things will change. Whether the discriminant is more, less than 0 or equal to 0. If it is equal to 0, then it will touch the x-axis exactly once. It will touch the x-axis exactly one time. So there is only basically one solution. There is only one solution or one answer to this where it becomes 0. But if it is more than 0, then you will see the graph will hit 2 times. There are basically 2 solutions. Or 2 roots is what you can say. Similarly, if it is negative, then it will not touch only, it will go like this. It will basically go like this. Basically, then there is no solution or basically no answer to that particular problem. Yes, there is no answer to that particular problem. Understood? All these things you should keep in mind. There could be graphs. One option will be from the top, one option will be from the below, one option will be from much below. You'll have to tick mark the correct option in the NEET examination. Students will think that, oh, sir, all the graphs are like this only, sir. I was not able to choose the option. So those students who know these theories will be able to select the proper answer. That is why I'm giving you everything in a very nice, colorful, attractive manner, so that when you download these notes from Telegram or from the PDF in the description later on, you will be able to enjoy these graphs and you will know every single graphical question in the NEET examination. Moving on to the next type. Guys. Yep. The next type is basically imagine it is something like this. Y is equal to, imagine it is something like y is equal to, imagine it is nothing but x cube. It is something like x cube. If it is x cube, the graph will be a curve. It is not a parabola. It is not a parabola. It is not a parabola, but it is a some kind of a curve. Similarly, if I show y is equal to x raised to 4, it will be even more steeper. It will be even more steeper. In general, if I say y is equal to x raised to 5, x raised to 6, it will keep on becoming more and more steep. Okay, so that's it. That's what you should know, that when the powers of x are increased, it will be a curved line. It is not a parabola, something which you should be aware of. Next important thing, next important graph which you should be aware of. Yes, let's go. Next important graph which you should be aware of is y is equal to 1 by x. 1 by x. This comes in many problems like potential, gravitational potential and so much more, magnetic field at a distance r and all of that. So when it is 1 by x, the graph is basically like this. The graph is basically like this. But if it is, let's say, y is equal to minus 1 by x, especially in gravity minus sign comes, then the graph is basically like this. In both the cases, it is a hyperbola. What is it? It is basically a hyperbola. So it will be a curve. It will feel like it is touching the axis, but it will never ever touch. It feels like it is going to touch both the axes. So this is hyperbolic graph when there is x in the denominator or minus x is there. All right. So both of these things, graphs are very, very similar, you can see. Sometimes you might probably get y is equal to, let's put it on the next slide, y is equal to 1 by x square. 1 by x square. That graph also is like this, but it is not a hyperbola. It is not a hyperbola. Please bear that in mind. It is not a hyperbola. Okay, everybody bear this in mind. When it is square, it is not hyperbola. When it is 1 by x only, it is a hyperbola. Otherwise, it is not a hyperbola. What if, sir, y is equal to minus 1 by x square, sir? Sometimes minus sign might come. Don't worry, that graph will be just a mirror image of this. It is also not a hyperbola. This is also not a hyperbola. Only x should be there. Otherwise, it does not work. Otherwise, it does not work. All right. So keep this in mind. Moving ahead to the next type of graph, which is very, very common. Sometimes you might also get e raised to something. Sir, y is equal to e raised to x is there, sir. What to do? If y is e raised to x, then basically think when x is 0, e is 1. When x is 0, e is 1. So the graph always starts from here like this. So it always starts from 1 over here, because when x coordinate is 0, e raised to 0 is 1. So it will start from here. So that is the catch. And sir, what to do if it is minus x, sir? Y is equal to e raised to minus x. It is as good as saying 1 by e raised to x. 1 by e raised to x. So such a graph basically starts from 1, because e raised to 0 when x is 0 is 1. 1 by 1 is 1. It starts from 1. When x becomes very large, this becomes very large. The y value becomes very small. So the graph goes something like this. It becomes very, very small value. It tends towards 0. So this is how the graph looks like. Keep all these things in mind. A lot of people think, sir, e raised to minus x. Sir, the graph will be like this. Many people draw this. No, this is not the graph for that. This is definitely not the graph for that. Okay? Keep these things in mind. Moving on to the next kind of graph, which you should definitely know, is basically standard thing, guys. Y is equal to sine theta. Y is equal to sine theta. How will the graph of sine theta look like? It will look basically like this. Y is equal to sine theta. It will look like this. Up, down, up, down, up, down. It will keep on continuing. This will complete at 2 pi radians. This will be nothing but 4 pi radians, right? This is nothing but pi radians. This is nothing but 3 pi radians. This is how the graph will look like. The maximum height and minimum height will be 1 and minus 1. 1 and minus 1. This is the graph of sine theta. Y is equal to sine theta. Similarly, my dear warriors, if by chance somebody puts some number over here, let's say y is equal to, let's say 4 sine theta. Y is equal to 4 sine theta. Then the graph will go up like this and it will come down like this. Okay, it will go up like this. It will come down also like this. Okay, it will come down like this. Yes, it will go like that. So this will go up by plus 4 and it will come down also by 4 units. So 4 on the top, 4 below. So that is how the graph looks like when you multiply a number outside. Then what about, sir, this graph, sir? Y is equal to cos theta. Y is equal to cos theta graph. The cos theta graph always starts with 1. It will go to 0. Then it will go to minus 1. Then it will go to 0. Then again plus 1. Then again 0. Then again minus 1. And this continues. So it completes one complete oscillation or one complete cycle in 2 pi radians over here. Remember, this is pi by 2 radians. This is 3 pi by 2 radians. And this is basically pi radians. The maximum height is 1, minimum height is minus 1. So that is how the graph basically looks like for cos theta. Basically, this is for cos of theta. Okay, right. So this is how the graph looks like. Keeps going up and down. It starts with a value of 1. Correct? Very good. Very good. Next important graph is y is equal to tan theta. Just in case you will not need it, but Chuma, I am giving it to you. So 0 to 90 degrees, it will go till infinity like that. This is at pi by 2 radians. Then again it comes from below and it goes like this and it goes on the top like this. So this is pi radian. This is basically 3 pi radian. And you will see that it will again come from here and this will go like this over here. Oops. It will come from here like this and it will go like this. So this is basically, why did I put 3 pi? My bad. This is supposed to be 3 pi by 2 and this is supposed to be 2 pi radian. So this is how the graph looks like for tan theta. Remember, at 90 degree, 270 degree, the value of tan theta is not even defined. So it is basically, you know, these snakes like curve like this, and it even continues even behind like that. Okay, so these are basically tan theta graphs. These are basically tan of theta graphs. Very good. Okay, now this basic knowledge everybody must know. Now let's go to all the important things. Starting off with, basically in units and dimensions there is no graph. Kinematics you have graphs. So let's see the graphs which are there in kinematics. And the most important graph is for slopes and all those things. So let's say we draw it here. Yep. So starting off with, imagine you have some graph like this, okay, and the axes mentioned are like this. This is position, this is time. This is position, this is time. Then if I basically draw a tangent anywhere, doesn't matter where you draw the tangent. Let's say you draw a tangent here and let's say the tangent goes like this. Let's say the tangent goes like this. Then this tangent which is there, this tangent which is there, the slope of this tangent, will be nothing but dx by dt. Now dx by dt, rate of change of x with respect to time, will be velocity. And if you measure this angle and let's say that is theta, then this velocity will also be equal to tan of theta. This will be also equal to nothing but tan of the angle made by the tangent with the horizontal line. Okay, so that is what the slope of position versus time gives you. The area does not give you anything. So don't even bother finding the area of position time. The area of this graph gives you nothing absolutely. Yep, it gives you nothing absolutely. Then when you go to some other graph like this, and let's say this time it is nothing but velocity versus time. It is velocity versus time. And then you find the area under the graph between two regions, from time number 1 to time number 2. From time number 1 to time number 2. Okay, if I find the area of this, the area under the graph, the area under the velocity versus basically time graph is given by integration. Area means integration. It is velocity with respect to time integration. Limits are those regions between which you are finding the area. That will give you nothing but delta x. Now delta x means displacement, so hence it gives you displacement. Hence it gives you displacement. The symbol of displacement, remember, is S. It gives you nothing but displacement. And if somebody draws a tangent to this particular graph, then the slope of this tangent, the slope of the tangent to the velocity versus time graph will give you dv by dt. dv by dt is acceleration, so that is also tan of the angle made by the tangent with the horizontal line. So area gives you displacement, slope gives you acceleration. Rate of change of velocity is nothing but acceleration. Correct. Yes. The area does not give change in displacement, the area gives you change in position, which is called as displacement. Okay, so delta x is change in position, not change in displacement. Okay, so be little careful there. All right. Next important thing, if I have acceleration versus time graph, some acceleration versus time graph, something like this is there, and you find the area. Here the slope does not give you anything, by the way. The slope does not give you anything. And here again you are trying to find the area under this particular graph from T1 to T2. So the area under the acceleration versus time graph is integration. I am integrating acceleration with respect to time from T1 to T2, and that will give me the change of the velocity. Not velocity, a lot of people make a mistake, change in velocity. It gives you change in the velocity. Now the exact same graphs and things you can also replicate it for rotational motion. So I'll tell you how. Instead of position over here, what you do, you make it angular position. Okay, so then what happens is, this will no longer be dx by dt. This will become basically d theta by dt. D theta by dt will not give you velocity. It will basically give you angular velocity. This theta and this theta are not the same. Don't get confused. So just probably I will put it as a different angle over here. Maybe I'll call this angle as phi. So it will be tan of this particular phi which is made over here. So rate of change of angular position is your angular velocity. Correct. Same way, if this graph I had to draw it in rotation, instead of velocity, I will be using the term angular velocity. And maybe it is also good point to not use theta over here. Let's say I use tan of phi. This is also phi. This will not be acceleration. This will not be velocity. Instead, this will be d omega by dt is nothing but angular acceleration. And this will be slope of the tangent of omega versus t. Rate of change of angular velocity is angular acceleration. And here also what will happen is, instead of area under velocity versus time, it will be omega versus time is nothing but integration of omega dt from t1 to t2. And what I will get is not delta x, I will get delta theta. This will not be just displacement, it will be basically angular displacement, and it will be basically delta theta. So that is your angular displacement, the area under omega versus time. Is that okay? So that is the big change. Very good. Similarly, instead of acceleration versus time, in rotation, what you will do is, you will make a small change. Instead of a linear acceleration, you will have angular acceleration, which is measured in radian per second square. Then the change that you will do is, instead of a, you will put alpha over here, and here also instead of a, you will put basically alpha integration with dt from t1 to t2. You will not get change in velocity. What you will basically get, come on guys, you can put it up in the chat box, delta omega. What is it? Change in angular velocity, not change in velocity, change in angular velocity. That is the big change. Cool, everyone? Awesome. Very nice. I hope you guys are enjoying this session, because I'm going to give you all the graphs in a neat manner and you will get it in a PDF later on. But if you just see the PDF, everything will go fly over the head like eagles and vultures. Okay, so that is the reason why you are watching this lecture, so that you understand. So you bring that vulture and that eagle down and make it into your pet parrot, or I don't know, your pet sparrow or something. Cool. Okay, right. So let's go ahead to the next particular graph. So in kinematics, these are the main graphs that you generally have, but sometimes you also get graphs based on kinematic equations. So what are those graphs which are there based on kinematic equations? Let me just show it to you. The first one is V is equal to U plus AT. This graph is very much similar to Y is equal to C plus mx. X is like time, y is like velocity, constant is like initial velocity, slope is like acceleration. So that's why you can just draw a graph like this, where this point is initial velocity and the slope of this particular graph is nothing but acceleration, and maybe at some given time, maybe the velocity is nothing but v. Maybe the velocity is nothing but v. That is how your graph would look like for the first kinematic equation. For the second kinematic equation, you basically find the area under this particular graph. And that area gives you displacement, and the displacement is nothing but area of the triangle plus area of the rectangle, which comes out as or first let me put rectangle first. Area of the rectangle plus area of the triangle. Area of the rectangle is, breadth into height, which is nothing but u into t, and the area of the triangle which is there, comes out as half into at square. Okay, you can derive that. So S is equal to ut plus half at square. That is the area under the velocity time graph. So that is another important graph that you should be aware of. Okay, cool. Let's move ahead. That is all that is there in kinematics. Okay, otherwise graphically there is not much that you will have. One more thing which you might probably get is the equation of trajectory. The equation of trajectory based questions, where the graph will be a parabolic quadratic function, and remember the equation of trajectory of a projectile motion is x tan theta minus half g x square divided by u square cos square theta, which is very similar to y is equal to bx plus ax square plus c, where c is 0 and a is negative. So obviously this graph, because a is negative, should be a downward parabola. Because the constant term only is missing, it must pass through the origin, and it is a quadratic equation, hence it's a parabola. So that is why the graph looks like this, and that is why the motion of the particle looks in this particular manner. That is why we say the trajectory, the path taken, trajectory means path of a body which is thrown is parabolic in nature. It is referred from this quadratic equation. Okay, by looking at the terms over here, you can see x square's coefficient is negative, constant term is missing. That is the reason why it is passing through origin and also going as a downward parabola. Is that okay? Very nice, very nice. Let's move ahead. Okay, next let's go to Newton's laws. What are the different graphs which we might find in Newton's laws? Friction, work, power, energy, and probably even in circular motion. So okay, so the next important graphs which you can find over here is, if you have a graph of momentum versus time, and the graph happens to be something like this, then the tangent drawn to this particular graph, the slope of the tangent to the momentum versus time graph is rate of change of momentum with respect to time. This is going to give you the force value at that moment. And if this angle is phi, you can also write it as tan of the angle made by the tangent with the time axis. Tan of the angle made by the tangent with the y-axis. That is what is the rate of change of momentum going to give you. Now, is there any other graph related to force? The answer is yes. In fact, if you have a graph of force with respect to time, then let's say that graph is something like this, I don't know, something like this, and then here you happen to measure the area under the graph. From one time to another time. So from time t1 to t2. So the area under the force versus the time graph is, area means integration of whom? Force with respect to the horizontal line, which is time, from t1 to t2, lower limit, upper limit. That is going to give you J, which is delta P. J is nothing but your impulse. Delta P is nothing but your change in the momentum. Is that understood, my dear warriors? This is what the graph is going to look like. Very nice. Then sometimes instead of force with respect to time, if the graph is force with respect to the position or the displacement, and let's say the graph is something like this, I'm just drawing something, and then again you find the area under the graph from one place to the other. So here we are trying to find the area. This is from x1, this is x2. Remember, these are coordinates. Area under force versus position or displacement. You will get integration force dx from x1 to x2. This happens to be the work done. Yes, W. And this work done is also change in the kinetic energy. This particular part, which is work is change into kinetic energy, that is your work kinetic energy theorem. Right? Work kinetic energy theorem. Change in kinetic energy is half m final velocity square minus half m initial velocity square. So that is how you find the work done, by finding the area under the force displacement graph for a variable force. Yes, perfect. Then you did this. Yes, Newton's laws. Yeah. Then another important graph which you must know, is this one of friction. Where you might have a body like this, and it is lying on a rough surface. And you are applying some push. So there is a push involved. And that push is plotted on the horizontal line. And there is frictional force which adjusts itself, which gets developed. So there is friction which will try to oppose the motion. So I'll plot it on the y-axis. That graph looks something like this. Initially, that friction keeps growing as you increase the push, and it is exactly going to go like this, making an angle of 45 degrees, till it breaches certain value, and then it instantaneously falls down to a constant value, and it is like this, and it is basically like this after this. This value, lower value, is kinetic friction. When it has gone into motion, when it has started actual motion. In the first part, it was basically stationary. It was basically static. It was not moving. And this value is basically your Fs max. This value is basically your Fs max. Remember, Fs max is coefficient of static friction into normal force, and your friction in general is less than or equal to this. At any given instant, your friction is self-adjusting, either this. All these values are less than the limiting force. All these values are less than the limiting force. Once it goes into kinetic zone, it is always a constant. And Fk is obviously mu k into m. Usually what happens? Usually you will see your mu s value is roughly equal to mu k value, which is why we approximately call it as mu. But remember, always mu s is less than the value of mu k. If more than, my bad, is always more than the value of mu k. If mu k is 0.37, this will be 0.38, 0.39, 0.4, like that. There is a small difference, but roughly we can take it as a standard value as mu. It is dependent on the materials of contact. It is dependent on the materials of contact. Correct. Very nice. This is a very, very important graph that you must know. Then the next important thing. Okay. In circular motion, I already told you about theta, omega, alpha and all of these things. Apart from this, there is no other peculiar graph that you need to remember in case of circular motion. All right. If some formula comes like centrifugal force is m omega square r. How does it depend on omega? Just example, centrifugal force is m omega square r. Do you see centrifugal force is directly proportional to square of omega? If it is square of omega, the graph will be basically parabola. If it is a question on how is it dependent on the radius or the distance from the center, then f is directly proportional to r. Oh, then it will be just a straight line. So accordingly, you will basically change your graph depending on what is the exact relationship asked. What is exactly asked. So that theory I have already given to you over here. That is completely basically formula based. This formula based, yes. Yeah, quadratic equation theory, discriminant, x cube, all these things I have already mentioned to you. One more extra graph that I might like to add over here is this particularly root of x graph. Sometimes root might also come. Okay, very, very important. For example, time is equal to root of 2h by g, or time period of a pendulum is 2 pi root of L by g. Plot the graph of time with respect to L. Plot the graph of time with respect to h. What do you do in those cases? Basically, we are referring to y is equal to root of x graph. Y is equal to root of x graph. What do you do in that case? I'll give a simple idea, simple hint. Square both sides. This will become y square. This will become basically y square is equal to x. Usually x was y square. Y was x square. Here y is not x square plus something. X is y square. So it is still a parabola, but it is not like this or like this. It is in this manner. So you will see that the graph would be basically like this. Actually, it is this kind of parabola, but you are not worried about this downward side. It is still going to be a parabola. It is still going to be a parabola, but it is not upward or downward parabola. It is a sideways parabola. Understood? So if a question comes like this, time period is 2 pi root of L by g, you can see time is directly proportional to root L. So this will be time, this will be basically your L. So time versus length axis will be like this. Time versus length graph will be like this. Directly you will be able to mark it. How many of you knew this, that you can also get sideways parabola? How many of you knew this? You can also get sideways parabola. Yep. Got it? Sometimes if you have y is equal to mv square, kinetic energy is equal to half mv square, then it will be a quadratic equation. You can use these graphs, right? Okay. So keep all these things in mind. Okay, this is done, right? Next one. Next one. This is work or energy, anything, and this is basically your time. And let's say I have a graph like this, and I end up drawing a tangent at some place over here. What do you think the slope of the tangent will give? The slope of the tangent drawn, to the energy, or basically the work versus the time axis. Whenever it is slope, it is rate of change. Rate of change of what? Y-axis. What is y-axis? Work. So dW. What is horizontal axis? Time. So dt. dW by dt. Oh, that's power. So it is basically going to give me power. So rate of change of energy or work with respect to time is going to give me the power. Exactly. Very good. Moving on to the next one. If by chance, let's say the graph is drawn for power versus time, and the graph of power versus time could be anything like this, then you will not find the slope, then you will be finding the area under the graph. You will be basically finding the area under the graph. So area under the power versus time graph will be what? Integration power with respect to time from T1 to T2. From T1 to T2. What do you think it will give me? Come on, my dear warriors. Yep. What do you think it will give me? Yes, it will give me. Very good. It will give me energy or work. Yes, it will give me energy or basically work which is done. So the work which is done by it. Yes, it will give you the work which is done by it. Keep this in mind. Cool? Everybody with me? Awesome. Next, moving up to the next few chapters. So if you remember, otherwise, you don't have any other graphs in Newton's laws or circular motion. Any other graph is again formula based. You have to just check whether it is proportional to some value or inversely proportional, square proportional. That's all which is there in the mechanics chapters, even in center of mass, collisions. Otherwise, there is no peculiar graph that you will probably see. Okay. Sometimes some special things might come, like probably this one. Let me show this to you. How does the kinetic energy of two bodies colliding with each other look like during elastic versus inelastic collisions? So if two bodies are colliding, then maybe before the collision they had certain total energy. Let's say like this. So there are two bodies, they are going towards each other or following each other, right? All of this is before the collision. Once they hit each other, their kinetic energy gets converted into temporary, other forms of energies. And once the collision is over, they might get back their original energy. So if they get back their original energies like the one over here, and they continue their journeys, so this is going this way, this is going this way, then it is E is equal to 1. Basically, it is elastic collision. But say for example, these bodies collide with each other, they lose some energy and they do not get back the same amount of energy as before. You will see that they go away from each other, but not so happily, not with so many speeds. So E is less than 1, but it is still more than 0. This is called as your inelastic collision. In the worst possibility, what will happen? They lose their kinetic energies and they never get it back. That's it, maximum loss of kinetic energy. So here E is 0, it is perfectly inelastic. It is basically perfectly inelastic collision. And you will see that there is maximum loss. there is maximum loss of energy in case of perfectly inelastic collisions. Perfectly inelastic collisions. This is a very, very important graph. In some questions, velocity time graph will be given and we have to find acceleration time. How do we solve those kind of questions? Yes. So, say for example, you know, your graph given is like this, and let's say this is velocity versus time, and you have to convert it into acceleration versus time. You have to convert it into acceleration versus time, or let's say reverse also can be asked. You have to convert it into position versus time. Example. These are also very, very commonly asked questions. Okay, no issues. We'll see how to solve them. Say for example, the graph of position time is like this. That means position is constant. That means velocity is how much? Velocity is the slope of this. Velocity is 0. So hence, the velocity graph will be like this. It will be flat over here. If the velocity is always 0, it is obviously not accelerating. Acceleration is 0. This part is clear? This part is clear? Okay. Let's go to the next variation. Let's say the graph is somewhat like this. Here, the slope which is there, it is constant and it is also positive. So hence, what you will do is, in this particular case, if it is like this, the slope is constant and it is positive, it will have a constant value. So V is some positive value. It's a positive value, but it is constant. That means it is not changing. So acceleration will be 0. Acceleration will be basically 0. If by chance the graph went down like this, here the slope is negative. Then the graph will be below over here. That's the only change. It will be below the time axis. And it will be constant. So V will be a constant negative value, and in that case also the acceleration will be 0 only. Okay, it will not be anything different. Till this point it is clear? Okay. Sir, what to do if something else will also come? Yes, we'll come to curves also now. So imagine the graph is something like this. Now this is, imagine a parabola. That means x is directly proportional to square of the time. So what will velocity be proportional to? It will be basically dx by dt. So since velocity is a dx by dt, derivative of t square is 2t. So it will be proportional to t. Time. That means it has to be a straight line like this. So here again you will see the slope is constant. The slope of this graph is acceleration. That means the acceleration will be positive constant. It will be a positive constant because it is going up like this. If by chance, let's say the graph was like this. Here x is proportional to minus t square. X is proportional to negative of t square because it is going down. Then instead of going up, I think the graph will be like this. So here the slope is constant, but it is negative. The slope is constant, but it is negative. Here it was positive. So in the acceleration graph, it will be a constant negative value. A will be a constant negative value. That is how you will solve it. Understood? Clear? Abhinya, I'm going to teach as many graphs as needed. For both 11th and 12th standard syllabus. Right? Clear? Very good. Yes. So this is how you convert from one graph to the another graph. Now, anything else that might come? Yes, sir, it can come. Let's say, for example, you have been given something like this. The graph is like this and like this. Or let's say it is like this and like this. Here, you should be a little bit careful. First, in this part, if you draw the tangent, it is having positive slope. In the second part, if you draw a tangent, it is having a negative slope. That means velocity is positive, then it is 0, then it is negative. Yes, it is becoming 0 also. It has 0 slope also. So for the first part, my dear warriors, what will happen? It is positive slope, so velocity is positive, then it is 0, then it is negative. So positive, 0 and then negative. You can see that over here, the values that you will get are positive. You can see that the values that you get over here are basically negative. Can you see that, my dear students? So this is how you have drawn the graph. Because the velocity is constantly decreasing, if you see the slope of this graph, that is itself negative. The slope itself is negative, so the acceleration will be a negative value. So the acceleration will be basically a negative value. Understood? Why it is negative? It will be some acceleration will be a negative value because the slope of this gives you acceleration. That's how you draw this. Yep. Right. Very nice. Let's move on to the next one. Sometimes imagine they can also combine few things here and there. For example, if they tell you, listen, angular momentum is a constant. And angular momentum is basically I into omega. That is basically a constant. So moment of inertia is inversely proportional to omega. That means the graph of I versus omega should look something like this. The graph of moment of inertia versus omega should look like this. Remember reciprocal graph, y is equal to 1 by x. So this will be nothing but a hyperbola. Got it? This is how you will figure it out. If by chance it is not this, it is something else. Let's say for example, it is, how does, let's say for example, rotational kinetic energy change with angular velocity. So rotational kinetic energy is nothing but half I omega square. Now moment of inertia is also, some number will be there like 1 by 2, 2 by 3, 2 by 5, depending on what object it is. And then you will have mr square into omega square. Now if kinetic energy's graph is asked with respect to mass, because it is directly proportional, I will say it will be a straight line because kinetic energy is directly proportional to mass. If it is asked with respect to r square or even omega square, then the graph would be like this because kinetic energy is directly proportional to r square or even kinetic energy is also proportional to square of omega. So this graph will be a parabola. Understood? That is why I gave you that theory before. Got it? Very nice. Yes. Yep. This will not be a hyperbola. This will be a parabola. Yeah. In the previous one, it was a hyperbola. Yes. So this is the kind of variations that you might get in different chapters. Okay. Different chapters might give you different kinds of variations. Apart from this, you don't have any other things over here. Okay. So let's move on to simple harmonic motion graphs. What are the different graphs that you get? 1 second. One second, guys. Okay, then in SHM, what are the different graphs that you can get? First important graph, guys, is this one. X coordinate or the position of the graph, x is equal to a sine omega t plus phi. A sine omega t plus phi. So the graph looks something like this. Yes, and remember, this is your time axis, this is your position axis. Then this particular thing is your amplitude, number one. Number two, when you go from here, from one point to the next point, exactly similar. This is basically your time period. That time period is nothing but 2 pi by omega. From one similar point to the next similar point, that is 2 pi by omega. And the shift, how much the graph has gone forward or backward, is dependent on this phi. It is dependent on this phi. So if phi is more, then the graph will shift ahead. If the phi is less, then the graph will shift. Sorry, phi is more, the graph will shift behind. Phi is less, then the graph will shift ahead. So it is exactly opposite. Understand that. So just to tell you what this phi does, if phi is basically positive, then the graph shifts behind. And if the value of phi is negative, then the graph shifts forward. So please bear that in mind. If this is some negative value, basically it has gone front. If it is positive value, then the graph has gone behind. So it works opposite. It works basically opposite. The next graph that you are going to have is of velocity, right? You will have of is velocity. Let's go to that also. And then also acceleration. So velocity versus time. This graph can be something like this. Velocity is a omega cos omega t plus phi. Here again it will be something like this maybe. Here this height is not a, it is actually a omega. It is basically a omega, and after one complete oscillation, after you get an identical point, that is basically 2 pi by omega, which is your one cycle or basically one time period. This is basically your one time period. That is for velocity. This is your max velocity. This is your max speed. Where do you get your max speed? You will get your maximum speed in a SHM at the mean position. When x is 0. Lastly, you will also have acceleration versus time graph. Yes, so if you have acceleration versus time graph, right? Say for example, acceleration is minus a omega square sine omega t plus, let's say, phi. Then usually the graphs go below first and then go on the top, something like this. Yeah, and then this one over here, right? This thing over here, this is basically a omega square. This values are basically max accelerations. Max acceleration is a omega square, and the max acceleration happens at extreme positions. Extreme positions means leftmost or rightmost, extremes positions. Again, from one similar point to the next similar point, whatever distance that you get is the time period, which is also 2 pi divided by omega, which is angular velocity. This is also something which you should be aware of. Correct, everyone? Yep. Then the next graph that you can get, yes, is of acceleration versus x, or even force versus x. So first of all, if you go with acceleration, remember acceleration is minus omega square x. So since acceleration is proportional to x, it will be a straight line but with a negative slope. So actually the graph goes from the origin like this. The graph goes from the origin and it is like this. So this is how the graph goes with a negative slope. Yes, with a negative slope like this. And if you talk about the force, force is minus kx. So again, force is proportional to x but with a negative sign. So the graph might be probably like this. It might again will pass through the origin. Again, it will have negative slope. But important thing is both of them will pass through the origin. That's how the graph looks like for force or for acceleration with respect to position. This was with respect to position. Remember, the earlier one was with respect to time. Completely different things. Completely different things. Very rarely they can ask this kind of question also, where you can have this. One second. You can have velocity, you can have velocity not versus time but versus x. This kind of graph is actually going to be an oval shaped. Very, very careful. Be very, very careful for this. Yes, it is almost like an oval, something like this. It is something like this. You will see that the graph extends till here and here on the x-axis. This is a max value of x, so it is plus a. Least value of x, which is minus a on the left hand side and the right hand side. This is the maximum value of velocity, so it will be plus a omega. This is the least value of velocity, which is minus a omega. This graph is an oval shape, which is basically an ellipse. Very rarely they can ask it, but if they ask, only you will be able to solve. Hello Tech, welcome aboard. Yep, very good, understood. Shuchi Mama Krishna, great. Yeah, this is another important graph for all of you. The next important graph is for energy. Let's go to that as well. Energy. So on the top, let's put energy, and then you will put time. Oh, no, sorry, not time. Position over here, that is basically x. First of all, potential energy, spring potential energy is nothing but half k x square. So the graph has to be a parabola. So the graph will look like a parabola also. It will go like this. The next graph I will draw is of total energy, which is always a constant. So that is why I will show it like this. The total energy is half spring constant into amplitude square, which is constant because mechanical energy is always conserved. The next graph is of kinetic energy, which will be exactly opposite of this. So it will go like this, and again it will come down over here. Notice very important points. This will be plus a, this will be minus a. The oscillation is happening between these 2 points. As it goes from here to here, spring gets extended, potential energy increases, kinetic energy becomes 0, and then again it comes back over here, and then potential energy is 0, kinetic energy is maximum. Again, potential energy is maximum, kinetic energy is minimum. The sum of the total energies will be constant. So kinetic energy, which is half mv square. Remember, the total energy is also nothing but your spring potential energy plus your kinetic energy. Yeah, it is the total mechanical energy of the system, right? This is again a very, very important graph. Also, there can be a question like this: where are these two equal? This is again a very common question. It is equal at what location, guys? It is equal at a by root 2. That is also one important question. A by root 2 on both sides. Minus a by root 2, a by root 2. The kinetic energy equals the potential energy. So at these points, kinetic energy equals the potential energy. Kinetic energy is equal to the potential energy. A very standard question. Yes, we'll come to energy displacement graph also. Yes, coming to that also. Yep, Meghna. Thank you, Janki, for all the love from Tamil Nadu. Thank you so much. Yep. Yes. All right. Then you have this graph. We'll come to potential energy graph also. Hold on. Here, you will have energy, here you will have energy, and here you will have time. And then if I ask you how will the graph of potential energy with respect to time look like, which is half k x square, x value is nothing but a sine omega t, so it is like a square sine square omega t, a square sine square omega t. So it will be like a sine graph, but it is square, so it will never be negative. So the graph actually looks something like this. It is like this. This is the graph of your potential energy. If you talk about kinetic energy, it will be half m velocity square. Remember, velocity is a omega cos omega t. So it will be a square omega square cos square omega t. M omega square is k. So it will become half k a square cos square omega t. So it is like cos graph, but it is positive always because of the square term over here. Half k square, half k square. Yes, it is the same. So cos graphs always start from positive 1. So it will be like this. This is how the graph of kinetic energy looks like. And if you draw the graph of total energy, obviously it has to be constant. So it will be like this. It will be basically like this. Yes. And the total energy will be half k a square, which is your total mechanical energy. This is how the graph looks like. Looks like a nice DNA structure. Wow, what a nice graph. Thank you, Krishna, for all the respect and love. Yesterday, I saw your love. Thank you so much, guys. I mean, really means a lot. All of you were waiting sharply much before 9 o'clock. Many of you had come from different cities, different towns, different parts of even Chennai also. And all of you came to Annanagar. It means a lot, and we had a lot of good time, a lot of academic content and fun time also. I mean, seeing everyone, it really made our day. Even though we were stressed out and we were not having sleep, we still were so energetic thanks to you guys. It is only because of you guys we had that much of energy. And yeah, we were even on the way back, we were discussing the same thing, how it was and how nicely we interacted. We should come there more often, and we should even probably meet in other cities. Probably I would love to visit all of you in my birthplace Salem very soon. And yes, other cities like Coimbatore, Trichy, you know, even Kanyakumari, there are so many students. Yep, Madurai, of course. I would love to come there. Yep. Oh, thank you, Kaushal Meena from Rajasthan. Wow, so cool, yeah. Which part of Rajasthan are you from? This is amazing. Amazing to see everyone learning from here and preparing really hard. Wow, this is too good. Okay, this was energy. Let's also go to another graph, which is energy versus displacement graph. This is also asked sometimes, energy versus displacement, potential energy graph, right? Okay, let me just create a duplicate of this. Yep. So if you have energy versus displacement graph and you happen to draw a tangent to this graph, the slope of the tangent drawn to this graph is du by dx, but that does not give you anything. Please understand that. It does not give you anything. In fact, if you put negative of the slope, negative slope of the potential energy versus x graph, that is minus du by dx. That is something, and that gives you the conservative force which is acting on it. The conservative force which is acting on it. Yes, this is your potential energy graph, relationship. The slope does not give you anything. The negative value of the slope gives you the conservative force. F is minus du by dx. In fact, this is also there at different places, like say for example, instead of potential energy, if I put it as just potential, and then I draw a graph, and then I happen to draw a tangent somewhere, and let's say that is phi over here, then if I measure the negative slope of potential versus x, this v over here is potential, please mind it, this is potential, not potential energy, then that will give me nothing but the field. Yes, that will give me the field, which is minus dv by dx, not the force per unit charge, which is the electric field, gravitational field. So many times you would have seen these kind of things. Yep, it is basically field. East Rajasthan. Wow, Kaushal. Wow, Pratibha, you are from Odisha. Oh, I should have guessed it from your surname maybe. Okay. Sir, how do we know NTA accepted our photograph in the form? If there was a problem, you would have got some issue, probably even in the city intimation slip, or generally they send some email, SMS, something like that. So if they have not sent you anything, that means there is no problem. If you are able to see your city intimation slip, then there is no problem. Okay, so be calm, be chilled only. All right. Yeah. All right. Very good. Very good. Moving on to the next one. And this is basically your stable, unstable and neutral equilibrium. Many times these kind of questions do come. So say for example, my dear students, let's say the graph is something like this. Oops. Okay. 1 second. Let's say the graph is something like this. Some graph it is, potential energy versus x. There will be some points where you will see it is an upward curve, which is like a peak here or here. At those points, in that region, the potential energy is maximum over there. And also, if you draw the tangent over there, the slope is basically zero. So remember one thing very clearly. If at any point on the curve of potential energy, let's say the slope happens to be 0, the force is 0, such a location is a point of equilibrium. Such a location is a point of what? Equilibrium. That is the place where the net force is 0. It is where it will be in equilibrium. Yep. All right. Very good. Vagdevi, you can check my old lectures because a lot of students want these kind of sessions now. So please check my other classes. Even you can check my JEE channel if you want to learn any topic, okay? Because now is the time we do a lot of problem solving. I'm pretty sure by now you should have also completed block 4. If you have not done it, please watch my any other old video also. That is perfectly fine. If you want, ping me, message me. I'll share you the video link which you can watch. Okay? All right. Now, these are the points obviously of equilibrium, but what kind of equilibrium? These are basically unstable equilibrium. Unstable equilibrium. And at unstable equilibrium, not only is du by dx 0, but also the second derivative of u with respect to x is a negative value. Is basically a negative value. When it is maximum, the second derivative, 2 times derivative, is negative. Similarly, at this point or even this point, what you will see is the slope is again 0. The slope is again 0, but minimum energy, so that is basically a point of stable equilibrium. Stable equilibrium. Yes. And here the second derivative d square u by dx square is a positive value. And there is one location where you will see for a long region the graph is flat. So u is constant. U is constant. The second derivative is 0. Then it is called as neutral equilibrium. It is called as neutral equilibrium. Neutral equilibrium. Okay. So keep these things in mind. Very good. Yeah. Thank you, Sirin Land, 43. Thank you. Okay, okay, great. Moving ahead now to the next part. So that is what is there in mechanics, most of it. There is one more thing which I can tell you, it is in gravitation. So one thing you have is the kinetic energy, which is for a satellite which is in orbit. It is half g m by r, which is basically negative of the total energy. Then you have the total energy to be minus half g m divided by small r, and that is yes, the total energy. And then you have the potential energy of the satellite, which is minus g m divided by the distance. There is no 2 over there, which is then equal to 2 times of the total energy. 2 times of the total energy. How do these graphs look like? First, starting off with the total energy, it is inversely proportional to r, but there is a negative sign over here. It has to be a hyperbola, so the graph will be probably something like this. It will go there and go like this. It will continue till infinity. Yes, this is how the total energy graph will look like. What about potential energy? It is double of the total energy, right? It is 2 times of the total energy. That means it is more negative. So you will see that the graph will be probably like this. Okay, it is slightly more difficult to draw it. It is something like this. This is the graph of your potential energy. The graph of your kinetic energy will be here. This is the graph of your kinetic energy. Why are these graphs here? Because of the minus sign. All these energies are minus sign, but only kinetic energy is positive. So actually only kinetic energy I will put it on the other side. That's it. This is kinetic energy. That is the only thing which is positive. Okay, that is the only thing which is positive. So that is how the graphs look like. Yep, very good. Keep it up. Okay, moving on, we'll come to different geometries like your ring, solid sphere, hollow sphere, etc. I will do it with electrostatics and all those things. We'll just move on to meanwhile thermodynamics, thermal physics and KTG and all those things, and fluid mechanics also we will try to do as many graphs as we can. Okay, so let's do fluid mechanics first, because fluid mechanics has very few graphs. So let's do that first. 1 second. Okay, in fluid mechanics, what are the different graphs that you will get? In fluid statics, there is no peculiar graph. Buoyancy is there, your hydrostatic pressure is there, Pascal's law is there, hydrostatic paradox is there, barometer, manometer. There you don't have any graphs. In fluid dynamics, when you go to equation of continuity, again there is no graph as such, plus there is no other graph in Bernoulli's equation and all those things. They are pretty formula based, diagram oriented, but no graph peculiar as such. Okay, if any formula based question comes, then you have to use my basic theory which I told you in the first 10-15 minutes of this particular lecture. For parabola, straight line, curves, how does the graph look like? In case of viscosity, viscous drag and all those things, there is only one peculiar graph that you should be aware of, and that is with relation to the Stokes law. When you drop any object in a viscous medium, eventually it achieves terminal velocity. Correct? So the graph of that looks something like this, and it goes here, and it reaches a certain value called as the terminal velocity, and this terminal velocity, you should all know, is 2 by 9. Here you will have r square g, density of the object minus density of the liquid, upon the viscosity coefficient. That is how the graph looks like for velocity versus time. Also remember, you can also have a graph of drag force, the drag force versus velocity. You'll be wondering, sir, what is that graph going to look like? Remember Stokes' law? The drag force is 6 pi eta r into v. The drag force is proportional to the velocity, so the graph basically goes like this. It is going to be a simple straight line. That's all. As simple as that. Yeah. Wow, Krishna, you have heavy rain and thunderstorms. You guys are lucky. Very good. Nice. Enjoy the weather and also enjoy the studies. Another important graph is in probably your surface tension chapter. Like, how is the excess pressure related to the size of the bubble? The excess pressure to the size of the bubble is related by 4s by r. So excess pressure is inversely proportional to r. So the graph looks something like this. So if you have a big bubble, it will have low pressure inside. You can see that big size, the size is big, then the pressure excess inside of it is low. But at the same time, if the size of the bubble is very small, then it will have high pressure. This is another very important concept which is there in surface tension chapter. Another important thing which you should know is with regards to the different sizes of the capillary tube, and how much height the liquid inside the capillary tube goes up. The height formula is given by 2s cos theta by rho g r. So height is inversely proportional to r. So the graph looks something like this. If you draw height rise versus the radius of the tube. So again, what it means is, if our tube is very wide, then the liquid rise is very less. But if the tube is very small, very thin, the tube is basically very thin, something like this, then the rise of the liquid is a lot. So it will rise by a lot of amount. That is your capillary effect. Correct? So this is the meaning of it. This is the main graphs which are there in fluid mechanics as such. Yep. Srija, I'll tell you, I have made a separate video for that. I don't know whether you have seen it. Go to the videos part. Just few days back. See this? Complete physics formula in 6 hours. It's not for 100 marks, it's for 180 marks. All the formulas are there. And I'll tell you what is the best part. In the description box of this particular video, I have posted the PDF also. The entire notes are there. I think it is there in the pinned section somewhere. Yes, it is there in the pinned section of the comments. You can directly download it. Okay, so do that. That is the best thing. Cool. All the formulas, all the chapters, 11th, 12th, everything is there. Okay, this is done. Right. Next, let's go to, what is this? Next, let's go to stress versus strain graph, Young's modulus and all of that, elasticity chapter. So in that, if you draw stress versus strain, let me create a duplicate first of all, or let me tell you some basic pointers first. When Hooke's law is valid, the stress value is proportional to the strain. The value of the stress by the strain is the modulus of elasticity. Now the modulus can be Y, which is Young's modulus, or it could be shear modulus, or it could be bulk modulus. This Young's modulus is for longitudinal deformation. Longitudinal deformation. This is basically for shear deformation, and this is for volumetric deformation. Volumetric deformation. Usually for fluids. Usually you will use it for fluids. Longitudinal deformation, usually you use it for solids. So Young's modulus, when you stretch something, compress something, longitudinal deformations, you will use Young's modulus. Shear is when you slide something, the force is parallel to the surface, the object bends like this. Bulk modulus is when you are changing the volume of a liquid, gas, etc. So usually for fluids. This is longitudinal stress by longitudinal strain, then it will be Young's modulus. Shear stress by shear strain, shear modulus. Volumetric stress by volumetric strain, it will be bulk modulus. It will be bulk modulus. I'm so glad, Pratibha, you guys enjoyed the formula revision session. Yes, predicted NEET paper is coming. We are just waiting for Diksha ma'am. Diksha ma'am is coming what is today? Wednesday, right? So day after tomorrow, she's already coming. Yeah. So then we'll be taking combined classes for all your mock tests, problem solving, etc. So only till tomorrow probably you will see our classes as a separate entity. But from Friday, we are all together. Your entire NEET team will be here. Yeah. And then we'll take classes. Yeah. We're just waiting for Diksha ma'am to come. Cool. All right. So that was your stress strain thing. Now remember, if you find the area under the graph, if you find the area under this kind of graph, what will that area under that graph give you? Area under the stress versus the strain graph. That area, my dear warriors, that area under the stress versus strain graph is going to give you the elastic energy per unit volume. Elastic energy per unit volume. Remember the formula for elastic energy density, which is half into stress into strain. The units of this is always joules per meter cube. How much energy is there per unit volume? Per unit volume. That's all. Yeah, that's all. So keep this also in mind. Now, when you extend this graph further, here remember this was where Hooke's law was valid. This is the point where Hooke's law was valid. That is, stress is proportional to strain. But there are points where stress is not proportional to strain. So there is a point till which you will see that the graph is a straight line, and this is basically the proportional limit. If I call that point as P, that P is proportional limit, and this region from O to P is where Hooke's law is valid. Hooke's law is basically valid. After that, you might see that the graph might not be a straight line. It could be probably something like this, okay? Or it could be probably something like this. Who knows? So this is basically going to happen till a certain point. Let's say I call it as E. I will call it as E, where the stress becomes sigma y. That E is basically called as the elastic limit. That means till this point the body is elastic in nature. So even if you remove the forces, it will come back to its original shape and size. It will come back. You pull something, leave it, it comes back. So O to E from this point to this point is basically called as your elastic zone. This is called as your elastic zone. And the stress that you get at this point is also called as the yield stress. This is a very important parameter when you design any machine or any device. The machine should be operating below the yield stress, so that if any vibration forces are there, the machine will not get permanently deformed, right? So the stresses have to be much below the yield stress. After this, what you get is the plastic zone, and here obviously it is not proportional. This point from E to, let's say I will call it as M, E to M. This point M is where you can give maximum load, maximum load point, and this region from E to M is called as the plastic zone, remember it. And here, if you remove the stress also, it will come back to a new point. Remember, here this was a two-way graph. Here also a two-way graph. If you remove it, it will come back. But here it's only one way. You can go like this, but you can't come back by the same route. If you remove the stress, it will come back to a new strain value. This point, there is no stress, but there is strain. No stress means no force. Strain is there means deformation is there without even stress. So this is called as permanent set. This is your permanent deformation, permanent set. Very, very important. Cool? Everybody till this point? And after this, what happens is the actual object breaks. So it fractures. It fractures at this particular point if you exceed the load. So this is the point where you can give maximum load, and this is also represented here as sigma S. So sigma S is also called as the strength of the material. Strength of the particular material. Keep this in mind. Okay, so this is your stress versus strain graph. Okay, I hope this is very, very clear. Awesome, awesome, awesome. Very good. Let's move on. So this is done. Now, after this, I think we should go on to thermal physics, right? So thermal physics, let's move on to. Okay. These people know. These people, they feel that they are very original. People are copying from us and they are telling we are copying from them. These idiots, they don't know who they are talking to, what are they. These are all paid people, and I know these people. I have seen so many teachers creating fake accounts and coming on to our channel and some other channels and spreading all kinds of nonsense. People are talking as if they have only invented Newton's laws. So any physics teacher who is teaching Newton's laws is copying Newton. So that is what it is. So we should create some original physics, some new Newtonian physics. Maybe people are flying in the air, and then that will be very original content. Amazing. Kudos. Slow claps to you guys. Very good. Congratulations. And you guys have been paying such people. So so all the schools in India celebrate annual day. Okay, so all the schools, imagine all the schools celebrate annual day. Sir, that school was celebrating annual day, they copied from us, sir. My school also did annual day. Oh my God, where do such people even come from? Seriously. I feel like laughing on these people, seriously. Okay, chalo, let's go ahead. Ignore these people. Anyways, coming up on the next graph is your temperature. Temperature versus length. Yeah. Thermal physics, right? When you heat something, the length will change. Yes. So temperature and length. So this is your temperature and your length. And the graph basically is a straight line. The graph basically is a straight line. And you will see that when you change the temperature by some amount, then the length also proportionately changes, delta L. And this delta L is equal to, you will have original length, alpha, and then delta T. That is how the graph is. And yeah, the graph feels like it is going to pass through the origin, but please remember one thing. This part of the graph which I draw is only a small part of the big graph. Actually, after this and before this, the graph becomes non-linear. The graph becomes non-linear. Only for a small portion, the graph is linear. In a big curve, just imagine, in a big curve, if you take a small part, it looks like a straight line. You take a small part, it looks like a straight line. You like a small part, it looks like a straight line. So only for small changes of temperature, it will look something like this. What is L0? L0 is the original or initial length. And what is alpha? It is basically the coefficient of thermal expansion. Keep this in mind. Coefficient of thermal expansion. Yes, correct. Yeah, very true. Vani ma'am used to say this. Correct. Thank you, Medico boy. I know. All right. Then in thermal physics, apart from that, you have temperature scales, calorimetry and all of that. Yeah, you have a phase change diagram, which is again very, very important. A lot of people ignore that particular phase change diagram. I don't know how many of you remember it. So on the horizontal axis, what you have is basically the time which you are giving the energy, and this is basically the heat supply rate. So the object under consideration is in the solid state. You are heating it, then suddenly it will convert it into basically a liquid. Then you heat it, then that liquid will increase its temperature and convert it into vaporized form or basically gaseous state. So heat supply rate versus time, or in general you can also combine both of this together and you can just put energy over here. That will be better. And then you can put temperature here. That is much better. Then the graph looks something like this. Observe. You keep on supplying the energy, the temperature will keep increasing like this till this point, and then you will see the temperature does not change. And slowly you will see after some time it has converted into a new form, which is new phase or new state, which is liquid state. And once it has converted into liquid state, again you will see the temperature will keep increasing, and then it stays constant for some time, and then finally it converts into gaseous form. That's all it is. This is how the graph looks like. This particular part is basically the solid phase. This particular part is basically the liquid phase, and this particular part is basically your gaseous state. Right? This is again very important. Here, you know, the liquid, if it is being cooled, the liquid will slowly cool and turn into solid. Here, if the gas is slowly cooled, it will condense into liquid. So here you will see both the states are in basically kind of equilibrium. Yes, both the states are in equilibrium. Wow, this looks like a flag of Argentina or something. Yeah, anyways. Both of them are in equilibrium, right? So this is, if you go this way, if you go like this, if you basically go like this, you are converting solid to liquid. That means you are melting it. This is called as your melting phase. If you go the reverse way, then basically it is called as solidification, or basically I'm just going to say freezing it. I'm going to freeze that object. Yes. If I go from here to here, I'm going to vaporize it. If I go the reverse way, what am I doing? I'm basically condensing it. Right? This is how these things look like. Next important thing is you should notice that why the temperature remains constant. Why the temperature remains constant here and why the temperature remains constant here. Because whenever phase change processes happen, always keep in mind that temperature does not change. It's an isothermal process till the entire process is over. Yeah, I will come to the phase change equation also. Hold on. Yeah, this point is called as your temperature for melting, temperature to melt or to freeze. This point is the temperature to boil, boiling point. This is the boiling point. This is the melting point. Correct. Now, what do these slopes give me? What do you think the slope will give me? Let's try to identify. Okay, so let's measure the slope of either this graph or this graph. So if I take the slope of this particular graph, let's say for example, the slope of this particular graph, slope of temperature versus heat, which will be dt by dq. Now dq, do not forget, is ms dt. dq, heat supplied, is ms dt. dt cancels. So what I will get is basically 1 by ms. That is what I will get. If you want, I can just call it as 1 by c. This s stands for specific heat capacity. This c just stands for heat capacity. Just simply put, heat capacity, not specific heat capacity. So the slope of this graph, temperature versus energy or heat supplied, you can see dt by dq. dq is ms dt. So dt cancels, it is ms or 1 by c. Mass into specific heat is just heat capacity. That is what it gives you. Got it? Gokulraj, please check out my old lectures, even from JEE channel, you can check it out. If you want, I'll share the link, ping me across, and you can check out those things. Now it's very important we do the full syllabus. Okay, we do all these extra things, formula revision, graphs, easy questions, difficult questions, twisted questions, mock tests, predictor paper. That is what we need to do now. Okay, so if you have any topic which is left out, please check out those classes. If you want, I'll put some specific video also on that or share the links for that. Okay, don't worry, it's there on this channel. All right, you can find it. If you're not able to find, I'll share you the link. Next important thing, when you're melting or freezing or when you're vaporizing or condensing, basically when phase change is happening, whenever your phase change process is happening, then obviously your temperature is a constant and you will use this equation, Q is equal to ml, where this is your latent heat, of vaporization, condensation, melting or freezing. This is at this point or at this point. Okay, so these are the things which you should be aware of in the phase change diagram. Everybody clear till this point? Shall we go ahead? Okay, so this is again there in your calorimeter part. Then when you go on to the next thing, which is let's say heat transfer. Let's go on to heat transfer. There you can have heat current on the y-axis, heat current on the y-axis, and on the x-axis you can have temperature gradient, and this graph looks something like this, a straight line. Yes, it looks like a straight line. What is heat current? Heat current means dq by dt. That is heat current. Temperature gradient, it is basically dt by dx. This is proportional, that is why it is a straight line. This is proportional, that is why it is basically a straight line. Now, important thing to note is what is the exact relationship between them? Well, we know it. dq by dt is nothing but k times a times dt by dx. K times a times dt by dx. Exactly. That is the exact formula. Everybody with me on this? Pakka? Ka dt by dx. K is conductivity, A is area. dt by dx, rate of change of temperature with respect to position. That's called as the temperature gradient. dq by dt, rate at which heat flows, is called heat current. This is your conduction equation. This is for conduction. Then You also have equations for radiation and stuff like that. Here you can have heat radiated per unit time versus temperature radiation we are talking about. Yes, we are talking about radiation, heat being radiated. This graph looks like this. It is not a parabola. No, it is not a parabola. It is just a curve, and you will see that the heat radiated dq by dt, okay, is proportional to the fourth power of the temperature. It is proportional to the fourth power of the temperature. Please mind it, not 2 power. No, it is fourth power. In fact, the heat which is being emitted per unit time is given by E times sigma times A times T raised to 4. In fact, you can also put Ts raised to 4 minus T raised to 4, that's okay. This is basically your emissivity. This is basically your emissivity. This is basically your Stefan-Boltzmann constant, which is 5, 6, 7, 8. 5, 6, 7 and 8. You put minus sign here. This is area, obviously, and that is the temperature. This is your main equation in your Stefan-Boltzmann law. This is your main equation in your Stefan-Boltzmann law, right? Another very, very important graph in radiation. Then another important graph in radiation is the Wien's displacement law, which looks something like this. If you draw the graph of intensity of the light versus the wavelength which is emitted, the graph looks something like this. You get a certain wavelength which is maximum in intensity. Let's say I call it as lambda 1 max. This has the max intensity. If now you change the temperature, let's say this temperature was the low temperature. Now I increase the temperature. You will see that this graph will shift and this graph will change. If I increase the temperature, it will go probably like this. It will probably go like this. You will see that this will be the new maximum intensity which is being emitted, and the product of the two temperature, let's say I call it T high. The product of the second time maximum wavelength with its temperature, let's say T high, will be exactly equal to the maximum wavelength emitted the first time multiplied by the temperature T low. Basically, what do I mean is lambda max into T is a constant. Is basically a constant. This is your Wien's displacement law. Wien's displacement law. Keep this in mind. Wien's displacement law. This is how the graph looks like. Yep. Right. Okay. Yes, I'll drink some water in a bit. Let me just complete this part. Yeah. So apart from this, in heat transfer, you don't have any other graphs. You have Stefan-Boltzmann law, Wien's displacement law, conduction, that's it. Then you go to thermodynamics. Yes, in thermodynamics, you have some amazing graphs. So let's see all those important graphs now. In fact, 1 second. Starting off with isothermal graphs. So pressure versus volume, pressure versus temperature, and let's say temperature versus volume, something like this. Okay, so we can create just a duplicate of this. Okay, so how do these graphs look like? For isothermal graphs, obviously temperature is going to be a constant. In fact, pressure into volume is going to be a constant. That means pressure is inversely proportional to volume. So the graph of pressure versus volume looks like this. Pressure versus volume will look like this. But this is at a lower temperature. This is at a lower temperature. If you increase the temperature slightly, then the graph essentially goes like this. It will go like this. This is at a slightly higher temperature. These lines are basically called as isotherms. These are called as isotherms. Any point on this line has same temperature. Any point on this line has same temperature. If I jump from this point to this point, I have gone to a higher temperature. I have gone to a higher temperature. Yep, very good. Then over here, how do these graphs look like? Let's have a look. So temperature is constant, so obviously the graph should be like this. If I go to a higher temperature, that means the graph should be over here. That is how it will look like. In this case, it will be probably like this. And when I go to a higher temperature, the graph will go over here. The graph will just go over here. Is that right? So that is how the graphs look like for isothermal graphs. Isothermal. Then let's move on to the next one. Yeah, so the next one can be, let's say, isobaric. Isobaric. So in isobaric, what will happen? The pressure will be constant. So that means volume by temperature will be constant. That means volume is directly proportional to the temperature. So volume and temperature graph will be like this. But let's say this is at some lower pressure. This is at some lower temperature. Or lower pressure, sorry. Volume by temperature, PV is equal to nRT. So V by T will be nothing but nR divided by P, which is the slope of this graph, which is basically the slope of temperature versus volume graph. So if I increase the pressure from low pressure to high pressure, denominator will increase, slope will decrease. That is the reason why if I increase the pressure, probably the graph will go like this. So this is for a slightly higher pressure. This is for some higher value of the pressure. In this case, how will the graphs look like? So basically isobaric, so pressure is constant. So probably like this and then like this. Over here also the same thing, low pressure and then high pressure. Pressure is constant, nothing great over here, right? So this is how your graphs will look like. Then when you go to the next one, which is basically your isochoric graphs, right? Next is isochoric graphs. Yeah. So in case of isochoric, what will happen? The volume is going to be constant. The volume is going to be constant. So therefore, pressure by temperature will be a constant. That means pressure will be directly proportional to temperature. So pressure and temperature graph, which is over here, it will be a straight line. Let's say I do it for lower volume. Now PV is nRT, so P by T will be nothing but nR divided by V, which is nothing but the slope of this graph. So if I increase the volume, the slope will decrease. So for a higher volume, it will have a lower slope. For a higher volume, it will have a lower slope. So in these cases, how will the graphs look like? Well, volume is constant. For higher volume, obviously higher volume here, higher volume here. This is how the graphs will look like, right? Very good. Then we can also have basically our, what do you say? Next one, which is your adiabatic graph. We can also have our adiabatic graphs. Remember, in adiabatic graphs, what will happen? It is the heat which is supplied, which is zero. So you can have pressure versus volume graph. Let's say, for example, pressure versus volume graph, and PV raised to gamma is a constant. PV raised to gamma is a constant, so it will again be like this. So PV raised to gamma is a constant. You can also have temperature versus volume graph and all of those things. It's again going to be just a curve. All the graphs are curved actually. All the graphs are going to be curved. So this is going to be like this, where TV raised to gamma minus 1 is a constant. TV raised to gamma minus 1 is a constant. Other things which you should definitely know in these graphs is like what other things are constants and not constants, or what is 0, etc. In this case, your delta U is 0. So the heat supplied is the work done, which is equal to nRT ln V2 by V1. ln V2 by V1. That is the formula for work done or also heat supplied. That is something which you should be aware of. Yeah, this is the same thing. Okay, this is the same thing. I'm just continuing over here. Next important thing in this case, isobaric graph. For isobaric graph, you will have work done is simply P delta V. Then your delta U will be simply NCV delta T, and heat supplied will be NCP delta T. That's the difference. Here in case of isochoric, the work done will be 0. Q will be equal to delta U, which will be both equal to NCV delta T. Both will be equal to NCV delta T. Then in case of adiabatic, Q is 0, delta U will be negative of the work done, and delta U we all know is nothing but NCV delta T. So hence the work done will be negative of delta U. You can also write it like that. The work done will be negative of delta U, which is nothing but negative of NCV delta T. One and the same thing. All these things please keep in mind. Yep. Okay. Maybe Serena. Maybe Serena. Yeah. Yeah. Someday we will have it. Yeah. Correct. Okay. Next important thing over here is if you have any PV raised to alpha, which is a constant, which is also called as a polytropic process. Polytropic process. The graph will be like this, and if you draw a tangent to the curve, the slope of pressure versus volume graph, which is dP by dV, will be negative always, and it will be alpha, that number which it is raised to, into P by V, into P by V. Why is this important? Is because if you extend this concept to adiabatic and isothermal graph, you can compare their slopes very easily. If it's isothermal, the graph is, let's say, like this. PV raised to 1 is constant for isothermal, and for adiabatic, PV raised to gamma is a constant for adiabatic. So for adiabatic, the slope is higher. For adiabatic, the slope is higher. You can see why. Because the slope of adiabatic graph will be minus gamma times P by V, whereas the slope for isothermal graph will be volumes power is 1, so just P by V. So this is gamma times more. Gamma times more. So this is very, very important. Slope of adiabatic pressure versus volume graph is nothing but gamma times the slope of isotherms. Very, very important. Gamma times more. That's why it is more steeper for adiabatic. Okay. here temperature was constant, and here heat was 0, so it was adiabatic. Very, very important. Awesome, Krishna. Yes, Sri Naland, correct. Very good. All right, cool. So these are the things. Anything else which we have left? And just think about it. These things. If you have pressure versus volume graph, and let's say the curve goes like this, then because it is going from lower volume to higher volume, please keep in mind the area under this graph is considered as positive because this is an expansion process. It is an expansion process. So the work done is positive. Whereas the same graph, if it went like this, then it is considered contraction process. Then the work is done on the system, not by the system. So the work done will be negative. In both the cases, please keep in mind this area is going to give me the magnitude of the work. This particular area that you see, the area under pressure versus volume graph is going to give me the magnitude of the work done. Not the sign. The sign comes from whether it is expanding or whether it is compressing, depending on that. And then you have this where, one second. Where if the pressure increases, decreases, and you come back to the same point, a cyclic process, pressure increases, decreases, etc. Again, some kind of cyclic process. But here it is clockwise. Then the enclosed area gives me the work done in that process, which is positive. In this case, if it is anti-clockwise, then this particular area, the work done will be negative. And in any case, remember, as long as it is a cyclic process, the change in the internal energy is 0 and the work done is always the heat supplied or absorbed. So the work is exactly Q, because Q is delta U plus W, and the change in the energy is never there because you are coming back to the same point, and U is a state function. Keep this in mind. Right. Perfect. Yes. All right. Very good. Yeah. Formulae, Aizia Mohammed, I have already done it. I'm not sure if you have seen it. I'll just show it to you right over here. If you go to the channel page, don't go to other things, go to videos directly. Go to videos, you will see complete physics formula revision, 6-hour class. All the formulas are there, and in the pinned comments, you will also find the PDF of the formulas. Okay. Today's session is concentrating mainly on the graphs, not on the formulas. If there are some formulas relevant to the graph, I am doing it. Otherwise, we are mainly concentrating today on graphs. For formulas, there is a separate lecture only altogether. Okay. Let me know if we have left out anything else in the 11th standard portion. I think we have done most of it. Just think about it. Yeah, thermodynamics, this is done. Slopes, area under the graph will give me work, right? All these things are done. You don't have anything other than that. Yeah, in KTG, you have one particular graph, and that is your Boltzmann graph. So here you have number of molecules, and here you have velocities, or basically speeds. You just call it as speeds, and that graph looks something like this, right? would have seen it. It looks something like this. A certain speed is maximum in amount, that is basically called as the most probable speed. Most probable speed. Let's say this is at some low temperature. Low temperature. If you increase the temperature, what happens is this graph will migrate like this. This graph will migrate like this. For a higher temperature, the speeds will become higher of all the molecules. This whole setup is called as Maxwell's speed distribution. Maxwell's speed distribution. Maxwell's speed distribution. And the most probable speed is basically given by root of nothing but, what do you have? 3 RT by m is for RMS. You have 8 RT by pi m for your average speed. And for most probable, you have it as root of 2 RT by molecular weight. That is the formula. That is the formula. Is that okay, everyone? Yeah. Gravitation, honey, will come to that. Gravitation, I'll be doing it with electrostatics. Cool. So thermal physics done, right? Okay. So now let's go on to equation of waves and all of that. Wave equation, if any graphs are there as such. So waves, sound, SHM was done. Yeah. In waves, you mainly have the wave equation, which you should be aware of. So the graph for the wave equation looks something like this. Y is equal to A sine kx plus minus omega t. This is what it is, where this A over here is the amplitude of the wave. The speed of the wave, whether it is going like this or like this, the speed of the wave is given by omega by k, right? And the next important thing is the direction. If it is plus, then it is going along the negative side. And if it is minus, then it is going on the positive side. Means if it is positive, then this wave is going towards the left. And if it is negative, then this wave is going towards the right. That is the change. Okay, so keep that in mind. A lot of people do a mistake over there. Yep, correct. Then apart from this, over here in wave equation, you don't have anything. Directly you have the wave speed formulas, power formulas, intensity formulas, interferences there, right? Then you have standing waves, organ pipes, and you have beats. That's it. So apart from that, you don't have much over there. No graphs as such. Direct formulas. Okay, so you just have direct formula based questions. Like say for example, in experimental physics, they might just tell you for a sonometer experiment. For your sonometer experiment, what is the formula of the unknown tuning fork that you have to find out? The frequency is given by n times v by 2l, where the velocity is nothing but root of tension by mu, and the tension which is there is root of the mass which is suspended into gravity divided by mu. So now if you notice, the frequency of the unknown tuning fork is directly proportional to the mass, but the tuning fork that you use is already having some particular fixed frequency. So if you take the length on the top, the length is directly proportional to m, because this f cannot change, the tuning fork's frequency cannot change, right? So length is proportional to root m. So how will the graph of length versus root or just the mass look like? The length versus mass graph will look something like this, because length is directly proportional to root m. It will be a parabola. Very, very important graph. If you see over here, length is also directly proportional to root of g. So if I had to draw the graph of length with respect to G, then the graph will again look like this. Length is directly proportional to root of G. That will be also a parabola only. It will also be a parabola only. Correct. Okay. Okay. I hope this is clear. Yes. Then you can also have mass per unit length graph versus mass and all those things. For example, if it is asked, how is mass related to mass per unit length? So m by mu is a constant. So m is directly proportional to mu. So more the thicker the string, more the mass you will need over here. So that graph will be a straight line because mass is directly proportional to mu. So it will be a straight line. So accordingly, looking at the formulas only, you can get the graphs. There is nothing great revolutionary about it. Same thing, you can also get experimental physics graphs here also. Once again. In resonance tube, in resonance tube experiment, right? Again, the frequency is nv by 2l and your velocity is nothing but root of gamma times p by rho, which is also gamma rt by m. Gamma rt by m. That is what your frequency is. The tuning fork is generally fixed. The temperature variations can be there. Accordingly, length will also change. So say for example, again, how will the length of the tube change with the temperature is asked. So length will be directly proportional to root of t. So again, this graph will be like this. So length is directly proportional to the root of the temperature. So it will be a parabola. Parabola. Sometimes you can be asked, the harmonic number, how is it related to the length? The harmonic number and the length are directly proportional to each other. So that will be a straight line. So L is directly proportional to L. So it will be a straight line. So these are basically formula based questions. So here you cannot, remember anything, or you cannot do it individually. If you know the formula and you know the graph theory, that's it. You can immediately predict how the graphs are going to look like. Otherwise, there are no specific graph based questions. Yes. Cool. Shall we go ahead? Yep. Awesomeness. Awesomeness. Yeah. So that is all that is there in the waves part. So I think we'll take a small break now before we go ahead. Yeah. To the 12th part, and we'll do electrostatics and gravitation and magnetism, all of them together, because that is preferred that we do it together. Yeah. So we'll do all of them together, right? So we'll take a small break and we'll return. It's 5:20, we'll return at 5:35. Not much is left in 12th, not many graphs are there, so that will happen very quickly. Okay. Meanwhile, please like and subscribe the channel. Yeah, like and subscribe. Okay, I'll see you in some time. Welcome back, welcome back, welcome back. Yes, the break time is over. I think we extended it a little bit, but that's okay. Yes. So I hope I'm audible and visible to all of you. And meanwhile, I had kept this slide for all of you only because there is mock test series which is going on right now, which is at all India level, and it is absolutely free of cost. So make sure you have registered for the mock test in case you haven't done that yet. These mock tests are available both in online and offline mode. Remember that. So make sure you make the best use of it. Best will be to do it offline. If you can't go to the center, at least do it online, because you will only also get the solutions and also you will get the analysis report card after the test is done. So make use of this, okay? Because last few days you have to solve more and more mock tests and problems, okay? Don't watch theory. Now theory watching is not so important. Watching problems, revision, one shots, that is what is useful. All right. So let's go ahead to the next few graphs that we have. We'll do electrostatics, gravitation and magnetism, most of the graphs together only because they are very much similar and related to each other. Then we'll go to, see, in ray optics you don't have any graphs, okay? In ray optics you don't have any graphs. In wave optics also you don't have any graphs as such. Main graphs are there in modern physics and electromagnetism. Otherwise ray optics, what is there? Formula based questions are there, optical defects that your telescope, microscope is there, prism, geometry is there. Those are mainly diagram based questions, so graph based questions are not there over there. Even in wave optics you have fringe width, interference, single slit experiment and the diagram based questions, but graphs as such it is not there, okay? Apparent shift, all these things, they don't have graphs. So remember, ray optics and wave optics do not have graphs, all right? If a graph question comes, it will be directly formula based like the ones I have shown you before. Modern physics has, and obviously electromagnetism till EMI, AC, obviously they have graphs. So let's see all those graphs. Ready for it? Okay. Sir is here. I hope I'm visible. DJ Tilu, nice to see you back. Yes, sir, I'm scoring 90 to 100. Is that possible for scoring 130? Yes, Yashasvi. You can push yourself to 130 with few things. From tomorrow, tonight I'm going to record a lot of things for all of you. I will tell you how to improve your scores. Yeah. Hello Meghna, hello Preeti, hello Krishna, welcome back Niksha, welcome back. Glency, yes, nice to see you back over here. Come on, so join back everybody. So let's go ahead for electrostats, gravity, all these things together. Okay. One second. Yes. So first of all, the graph for single point charges. For single point charges, what are the different graphs that you can get? One is the graph for electric field or gravitational field. It is either like Gm by r square or it is kq by r square. So the graph will be like this. It is not a hyperbola, it is just some curve. Then the graph is there for your potential, which is minus Gm by r or kq by r. So if it is kq by r, then you will see the graph will be like this. This is for electrostatic potential. If it is gravitational potential, the only difference is it is negative, so minus Gm by r. So the graph will be like this. So this is for gravitational potential. Remember, both these graphs will be a hyperbola. Yes, both these graphs will be a hyperbola. Yeah, because it is inversely proportional to r. So this is a hyperbola. Is that okay? So for potential it is hyperbola, for field it is definitely not a hyperbola. It is just some random curve. That is one thing for point charges. Then when you go to dual charges or a pair of charges. So when you go to a pair of charges, you generally have the concept of force first. So the force is either G m1 m2 by r square, or it is K q1 q2 divided by r square. So the graph is just a curve for the force with respect to distance. This is distance over here. This is force, let's say, in this situation. Okay. In the previous one, this was field and this was your distance. Okay. This was your distance. Okay. Similarly, for potential energy, how will the graph look like? So again, for potential energy, it is K q1 q2 divided by r, that's it. And the graph will be on the top for electrical potential energy. That is also true only if both charges are positive. So actually speaking, it might be even down. So this is actually true if both charges, if both charges are positive or both charges are negative, then it is fine. Else it will be downwards. If one is positive, one is negative, or if there is one mass here and another mass here, and we are talking about gravitational potential energy, which is negative. So minus G m1 m2 divided by r. And again, let me remind you that this graph is obviously a hyperbola. Okay, keep these things in mind. Masses will also attract, positive, negative will attract, so it is down. Anything which is repulsive, positive, positive or negative, negative, it will be on the top. Both the green and the red ones are hyperbolas. Is that okay? Yes, very good. Next important graph. Is for a shell. Gravity or electrostatic really doesn't again matter. So for a shell, okay, if you talk about gravitational field or electric field, again there are two parts in it. Inside it is going to be 0. Outside it is just going to be K Q divided by r square or G m divided by r square. Okay, so inside it is 0, outside it is going to behave like a point charge. So the graph will be like this till r, and the moment r comes, it will go straight up and it will go like this. It is not a hyperbola, it is just some random curve. Again, this graph is versus distance. Here I have drawn it versus the electric field. What if I draw it with respect to the potential? Now the potential graph, remember, if you are inside, it is a constant and it will be basically K Q divided by capital R, or it will be minus Gm by capital R. And when you are outside, it will behave like a point mass or point charge. It will be just Kq divided by small r or minus Gm divided by small r. So what do I mean by that is, the graph, if you are talking about positive charge or in general electrostatics, it will be constant, and then when you go outside, it is inversely proportional to r. So it will look something like this. It will be constant. This is for a positive charge. We are talking about potential. And then once you go out, it will be inversely proportional. So it will go like this. Yes, this is a hyperbola. But if you are taking a negative charge, mind it, if you are taking a negative charge, it will be constantly negative till this point, and again it will go like this. Yes, this is also a hyperbola. This is true if you take a negative charge or even a mass, because for negative charge Q will be negative. For mass, anyways, the negative sign is already present over here. So I'll just extend this over here. Okay, everybody fine? How these graphs look like? For potential, this is. Okay, all this is for potential. Fair enough? This is for a shell. Yes, very, very important. Moving ahead. Let's go for solid sphere. Let's go for solid uniformly charged sphere or a solid mass. For a solid sphere. Again, when you are inside, the electric field when you are inside is proportional to R. So actually it will become KQ small r divided by R cube, or in gravity it is Gm small r divided by basically R cube, right? So the graph for electric field goes up like this and then goes down like this. It's just a curve, and here it is obviously a straight line as long as you breach the surface mark. So with radius, yeah. Outside it is inversely proportional to R square, we'll come to that, but inside it is just directly a straight line. You can see, because electric field is directly proportional to small r. The moment you go out, it is the standard formula. So it is KQ by R square or Gm by basically R square. This is how the graph looks like for a solid sphere, which is uniformly charged, or a solid chunk of mass. Outside it is inversely proportional to R square. Sorry, I have to put small r square. Talking about potential, my dear warriors, again, depending on whether it is a positive charge or a negative charge or gravitational mass, things will change. So if you take electrostatics, it is KQ divided by 2R cube, this is inside by the way, into 3R square minus R square, and for gravity it is minus Gm divided by 2R cube and 3R square minus R square. This is inside, and when you are outside, it is going to behave like a point mass only. So it is just KQ divided by R for electrostatics. For gravitation, it is minus Gm divided by R. So how does it look like? If you take electrostatics for example, inside it is quadratic in nature, outside it is hyperbolic in nature. So the graph looks somewhat like this, guys. It will go like this, parabola, and then a hyperbola. Yes, this part is a parabola and this part is a hyperbola. So this is potential versus your distance curve. If you take gravitation or negative charge, it is exactly opposite. It will go like this till here and then it will go like this. That's it. That's the only difference. So this is for a negative charge or for a mass. This graph is for a positive charge only. It will be on the upper side. Is that clear, my dear students? I think Diksha ma'am will start at 7 o'clock. That's what she told. I'm not so sure. Yeah, I think she's going to start at 7 o'clock. Okay. Next important thing is, let's go ahead. For a linear charge. In gravity, there is no linear charge. So the electric field for a linear charge distribution, the electric field formula is only there, which is nothing but 2 times k lambda divided by r. So the graph is just like this and it is a hyperbola. So this is nothing but your electric field versus your distance. That's all. 2k lambda by r. This is also the graph for magnetic field. If you remember, even for magnetic field due to a long wire, it is nothing but 2 times mu naught by 4 pi, current divided by r, or mu naught I by 2 pi r. So this is also true for magnetic field due to a long wire, that is exactly like this. It is inversely proportional to R. Okay, so same graphs are getting repeated at two places. Then for a ring, how does the graph look like? In fact, I think for a ring we should use different one. Yeah, for a ring which is either charged or having some mass, if you talk about the field formula, right? The field formula is given by kq x divided by r square plus x square whole raised to 3 by 2, or in gravitation it is gmx divided by again r square plus x square raised to 3 by 2. So how does the graph look like for the field? How does the graph look like for the field versus any point on the axis of the ring? It looks something like this. The field is 0, so it will look something like this. It looks something like this. The field is 0 when x is 0. So x 0, field 0. X negative, E negative. X positive, E positive. So when x is positive, E is positive. When x is negative, E is negative. So this is how the graph looks like passing through the origin. When you draw the graph for potential, potential, how does it look like? So for potential, my dear warriors, the graph should be something like this. Again, if it is a positive charge, so it is k divided by root r square plus x square. So the graph just goes up over here and then calms down. So it goes up over here and then it calms down over here like this. This is true if it is a positive charge. But if it is a negative charge or gravity, then it is minus gm divided by root r square plus x square. So the graph will go down like this and it will calm down over here. This is true for a negative charge or for even a mass. Because the sign is negative, charge is negative, again the sign becomes negative, it will go down over here. Okay? Yes, that is how it works. Cool till this point? Everybody with me on this? Very good. This is for a ring. Then, sheet and all, you don't have graphs. Dipole, again, you don't have graphs. Again, if you talk about point charges and everything, that is also done, right? Spheres, shells, everything is done. All right. So I think with this, then we should go to the next thing of magnetic field only, I feel. Yeah. There is one very important graph for magnetic field due to a long wire, but inside and outside both. Magnetic field due to a long wire. Very, very important graph. So how does the magnetic field look like? When you are inside the wire, it is mu naught I small r divided by 2 pi capital R square. And when you are outside, the magnetic field is mu naught I by just 2 pi r. So you can see it is directly proportional to r here, and here it is inversely proportional to r. So directly proportional to r means it will be a straight line inside, and when it goes outside, it becomes like this. Yes, outside it is a hyperbola and inside it is just a straight line, and the value change happens exactly over here at capital R. So this is the graph of magnetic field versus distance. Magnetic field versus distance for a very long wire which is carrying current. Yes, you can see it is very much similar to this particular graph over here, which we have seen for solid sphere, straight line, and then it is inversely proportional to this, right? So we have seen that right over there. Correct. Very good. So apart from that, which other graphs are there? Apart from that, You have torque on a dipole and potential energy of a dipole graphs, dipole in a field type of questions, dipole in a field type of questions. So say for example, torque is asked. Torque is P cross E, which is P sine theta. In case of electricity, or in case of magnetism, it is MB sine theta. So the torque graph will be just like the sine theta graph. So it will be just like this. It will just be like this. Just go up, 0, just go down and come back to 0. So yeah, this is more than enough for you to draw because you have completed one complete cycle. So the torque is maximum at 90 degree. So this is the maximum torque which you can get, and 0 and 180 degree, they are the two different points of stable and unstable equilibrium. So 0 degree is basically stable equilibrium point when torque is 0, and 180 degree guys is the point of unstable equilibrium, Similarly, you have the equation for potential energy, which is minus PE cos theta, or in magnetism it is minus MB sine theta. So it will basically become negative of the cos graph, So it will probably be like this, let's say. So it has to pass through this, go over here, and it has to go like this and go over here. Yeah, one cycle is completed. You can see at stable equilibrium, you can see it has minimum potential energy, which is actually minus P, and at unstable equilibrium you can see it is unstable, so maximum potential energy, which is equal to plus P. This is potential energy, not P dot E. This is plus P, or even you can use plus MB. Here also you can use minus MB. Either this or that, depending on electricity or in magnetism. These are the dipole in the field graphs, which you must be again aware of. Yep, very, very important, right? So these kind of questions can come in graph. Yep. Okay, so that is also done. Main geometries are done. Okay, for toroid, solenoid, you will not get questions on graphs. They are direct formula based questions. Ampere's law, Gauss's law, they also are not graphical based questions. They are directly application based questions. So they are not graphical based. Then dipoles is done. Yes, this is done. Fair enough. Okay. Then let's go to some magnetic properties related graphs also. Some magnetic properties graphs can also come, guys. Okay. One such graph is for susceptibility graph with temperature. So if you draw the graph of susceptibility versus temperature, this is susceptibility graph. Okay, so the susceptibility graph depends on the type of the material. If it is a paramagnetic material, then the graph is like this. Then the graph is basically like this. Susceptibility is inversely proportional to temperature. Yes, this is called as Curie's law. More the temperature, susceptibility reduces. Yes, it is a hyperbola. And if it is a paramagnetic material, this is paramagnetic material, very, very important, not for other things. If it is a diamagnetic material, then susceptibility is negative. So please keep that in mind. It is a negative value. This is true for diamagnetic material only. It behaves like this. Yes. And obviously it is constant. It is basically independent of the temperature. No matter what you do with the temperature, it is always constantly negative only. There is no change in that. Whereas for ferromagnetic material, then the graph of susceptibility it's very, very high initially, and then comes a point where the susceptibility changes just like a paramagnetic material, because the material only becomes paramagnetic. So the graph goes like this. Till here it is ferromagnetic in nature, and after this it becomes or behaves like a paramagnetic material. So actually this temperature at which the behavior transits from ferro to para, that is called as the Curie's temperature. That is called as the Curie's temperature. Very, very important. That is called as the Curie temperature. Keep this in mind. Okay. Here it behaves like a normal paramagnetic material, just like I have shown over here. Yes, it is a standard hyperbola. So this Curie's temperature, I can call it as Tc. So here the behavior is susceptibility is inversely proportional to T minus this Curie's temperature, T minus Tc. Okay, because you have to shift the origin from here, because that is how the graph behaves. So that is the correct formula. Yeah, correct. Very good. Then the next important graph that you might need. Okay, one second. Let me just duplicate this. Is how the intensity of magnetization varies with magnetic intensity. Two different things. So over here we have H, which is magnetic intensity or magnetizing field, what it is called, and that is basically your nothing but external field divided by mu naught, that is magnetizing field. And over here I have I, which is also called as intensity of magnetization, intensity of your magnetization. This is magnetic moment per unit volume. Keep this in mind, magnetic moment per unit volume. So how do these graphs change? If it is a diamagnetic material, when H increases, you will see that intensity of magnetization increases, but reverse way, because it always repels. So that is why the graph goes like this. It is in the fourth quadrant. And when you remove it, it will again get demagnetized and it will come back over here. So that is why the graph is over here. If you give reverse direction, magnetizing field, then I is in the positive direction. Again, it is reversible process, meaning if you remove the magnetic field from outside, the magnetization will also completely go off. So it's just a simple straight line with a small slope. Because it gets weakly magnetized in a repulsive manner. This is for diamagnetic. For paramagnetic, it is exactly opposite of it. It's a small slope and it is also reversible, because paramagnetic materials, if you remove the external field, it again comes back to its original state and it will get demagnetized. You magnetize it, it will get magnetized in the same direction. So H positive, I positive, negative, H also negative. So it's reversible. The only problem is with the ferromagnetic material, where if you magnetize it, then the magnetic intensity also increases, but it is only one way. If you remove it, then it comes back and it is now permanently magnetized. So this is how it is going to behave. And this point, how much ever magnetization intensity it retains, it is how much it is retaining. So it is retentivity. How much intensity of magnetization is retained. How much magnetization has been retained, that is why it is called as retentivity. So it is not a reversible flow. You can see that going path and coming path is not the same. This is only true for ferromagnetic materials. ferromagnetic materials. Okay, so this was true for paramagnetic materials. Very, very again important curve. Yep. Or today in the exam only they asked it. Wow, interesting. Very nice. Okay. Apart from that, in magnetic materials and all these things, you don't have any other graph. Okay. Magnetic polarities, magnetic charges, no. Coils, nothing. Okay. Yeah. Directly in capacitors, Q is equal to CV. Capacitance formulas are there. Dielectric strength, nothing. Series parallel, nothing over there. See, you can get questions like what will happen if area is increased, how will the capacitance change? I mean, these are formula based questions. So formula based questions you cannot draw all the possible graphs now, because on the spot only you have to think, okay, capacitance is epsilon naught A by D. Capacitance is proportional to area. So if area increases, capacitance increases. So it will be a straight line. Capacitance is inversely proportional to D. So if distance increases, capacitance decreases. So it will be inversely proportional. So it will be a hyperbola. So that logic will come only if you know the formulas. And if you remember, I have made a separate formula session. So in case you have not yet seen it, please check it out. Okay, it's rightly placed over here in the video section. Complete formula revision for physics, one last lap with PDF attached. Okay, so you can check that out. Okay, great. Then, yeah, we'll come to modern physics. Hold on. Yes, we'll come to modern physics. In capacitors, I don't think anything is there. We can have Ohm's law based questions like this. In Ohm's law, you can have things like this, where, say for example, this is voltage, this is current. If the graph is a straight line where voltage is proportional to current, it is called as a ohmic device. It is called as a ohmic device. But there are certain devices where the graph might be like this, or maybe the graph is like this. Who knows? It could be something like that. Who knows? So these are basically non-ohmic devices where the voltage is not proportional to the current. Usually how it happens is, even if you have a non-ohmic device or ohmic device, you can directly find the resistance by looking at the current and the voltage values. Say for example, at this particular current, okay, let me show it on another graph maybe. Say for example, this is current, this is voltage. It could be a straight line, it could be a curved line, really doesn't matter, okay. Some graph is there for some device. Say for example, I note down, okay, this is the voltage, this is the current. I can find the resistance at that point. The resistance, remember, because V is equal to IR, resistance is voltage by current. This is just simply put the resistance. And the resistance can change if it is a non-ohmic device, because the curve is changing, voltage will not be proportional to the current. So obviously for non-ohmic devices, resistance is not constant. But for ohmic devices, your resistance is a constant value. Example, conductors, ohmic device. Capacitors, inductors, and all such other things, even semiconductors, vacuum diodes, they are non-ohmic devices. Their voltage and current, they change in a very different manner. Okay, so they are non-ohmic devices. Now, you have another term over here, which is basically you measure a small change in a particular region. Say for example, from here to here, you measure the change. Say example, like this. The height is basically delta I, the base is, let's say, delta V. If you measure delta V by delta I, what you get is not the same old resistance. This is called as dynamic resistance. Sometimes questions have been asked on dynamic resistance also. This is called as dynamic resistance. Lot of people find the slope of these graphs and they think it is this resistance. No, the slope of this graph is not going to give you resistance, it gives you dynamic resistance. Keep that in mind. Slope of voltage current graphs do not give you resistance, they give you dynamic resistance. Resistance is found by actually substituting the values and dividing them. That gives you the original, static resistance. Correct. Keep this in mind. Very, very important. Also, keep this in mind that, say, resistance variation with length and area is asked. It is also again completely formula based. Okay. So, if resistance formula is given as rho L by A, depending on what is constant and what is not constant, things can change. See, if area is constant, then resistance is directly proportional to length. If length is constant, then resistance is inversely proportional to A. Here, length is a constant. Here, area was a constant. But be careful. I'll tell you why. Things can change drastically if volume is constant. Actually, one second. If volume is constant, because if volume is constant, volume is area into length. So it will become rho L by, instead of area, I can put volume by length. And here also I can put rho, instead of length, I can put volume by area. So it will become rho, length I will put it as volume by area. So it will become A square. Now this graphs only will change completely. Observe how. If area is constant, if volume is constant, my bad. If this volume is constant, then resistance is directly proportional to L square. And resistance is inversely proportional to A square. Resistance is inversely proportional to the square of the area. So it completely depends on whether volume is constant or length is constant or basically area is constant. Accordingly, things will change. Things will definitely change. Correct. Yes. Also, what you need to remember, is if you draw a graph of resistance with temperature, a lot of people feel it is a straight line, but actually it is not. It is actually a curved line. If you take a small region of it, it will be a straight line. And in that small region, there is a change in the resistance, there is a change in the temperature, and that change in the resistance is given by original resistance into alpha into delta T, like in thermal expansion. So this formula, which is RT is equal to R naught into 1 plus alpha delta T, is only valid for small range of temperatures. Correct? So this is your coefficient of thermal resistance. Is that okay, everyone? Yeah, keep that in mind. Yeah, very, very important. Please remember, this graph, whatever I have drawn, is actually for a conductor. This is actually for a conductor which has positive value of alpha. If you draw a similar graph for semiconductor, that graph will be probably like this. This is for a semiconductor. semiconductor. It has negative value of alpha, meaning when you increase the temperature, the resistance will go down. When you increase the temperature, resistance will basically go down. Correct. Correct. Very good. Excellent. Awesome. Awesome. Then you can have many other such graphs like say for example drift speed versus relaxation time, etc. For example, drift speed is E by m into tau. If the field is constant, then drift speed is directly proportional to the relaxation time. So the graph will be a straight line. Drift speed is directly proportional to the time constant, right? So this is one such graph which you can make. Everybody with me? Very good. Correct. Okay. If you ask me, how is drift speed related to current? Well, current is equal to NVIDIA. Oh, current and drift speed are also proportional. So that graph will also be a straight line because yes, current will be directly proportional to the drift speed. It will be also a straight line. Maybe the slope could be different. Yep, correct. If you ask me how does drift speed change with area or something, how does drift speed change with area? Well, drift speed and area multiplication will be constant if current is constant. So the graph will be a hyperbola. This will be a hyperbola. If you draw drift speed versus area, drift speed versus area, it is 1 by A. So all these things are again completely formula based. You cannot sit and by heart it. If you know the formula, end of story. If you know the formula, you know the exact relationship, right? Very good. So those things, there is no point discussing it separately. Another important graph which probably can come is for battery's terminal voltage versus the current. So if you put voltage over here and maybe current over here, generally we put voltage here and let's say we put current over here, this graph will be a nice straight line. Yes, it's a beautiful straight line. Now you should also understand that if you take any random point on the graph, let's say you take a point over here, the voltage is V, current is I, this voltage will be nothing but E minus IR. It's of the form y is equal to mx plus c. It is like straight line equation, voltage and current. Yeah, straight line equation, y axis, x axis. So yes, it matches why it's a straight line. Now what is important over here is what is this point versus what is this point. At this particular point, there is voltage but there is no current. So at this particular point, current is 0, voltage is there. That voltage will be equal to E. Basically, this is an open circuit. That is why they say the terminal voltage for an open circuit is the EMF. When no current flows, whatever voltage you measure is the actual EMF of the battery. Then you might be wondering, sir, what is this one? What is this point? Here, the voltage is 0. Current is maximum. When will that happen? Basically, the circuit is shorted. You connect the positive to the negative. By the wire equalizes the potential. So there is no voltage difference only across the battery. So the current is maximum and this maximum current will be EMF by the internal resistance. Yes, this is your internal resistance only. Internal resistance. That's when you will get maximum current. So if these graphs are given, you can find EMF, internal resistance, everything. So this is a very important graph for current versus this voltage is also called as the terminal voltage. Terminal voltage. Is that okay, my dear warriors? Everybody with me? Yeah. Is it possible that current flows without voltage? Yes, it is definitely possible. Without potential difference also, current can flow. If you have thought otherwise, let me tell you, it is not true. Okay? Right. Very nice. Great. So, in this, I think this much is there. What else will be asked? Yeah, magnetism, we can actually have one more, moving coil galvanometer as well in current electricity. So this moving coil galvanometer, remember, a galvanometer is a device which measures deflection when more current is passed through it. More the current, more the deflection. In fact, the deflection is proportional to the current passing through the galvanometer, and this theta, what is this theta? The deflection, what is Ig? It is basically the current passing through it, is given by NBA divided by K, and this is into Ig. So if you draw the graph, it will look something like this. It is going to be a straight line for deflection versus the current in the galvanometer. What is N? Number of turns. What is B? Magnetic field. What is A? Area of the coil. What is K? Torsional spring constant inside the galvanometer. So this kind of question can also come. This kind of question can definitely come. Right. Very good. Awesome. Okay. Very nice. What else can we be asked? Magnetism. I think most of it is done. Yeah, we can talk more about also magnetic moment versus radius and all of that in case some questions come on it. So see guys, for magnetic moment of a coil, what kind of questions can come graphically? Usually our magnetic moment is nothing but number of turns into current into area. So if it is written down as pi r square, then if I write magnetic moment versus our r, I am allowed to use as many wires as, or as many length of the wire as I want, and I can change the number of turns, I can change the radius of the wire. So then the graph will be basically like this. It will be proportional to r square if wire can be made longer. If wire can be made longer, there is no problem in that. If I can increase the number of turns, so this was the first part, m is directly proportional to r square. If I'm allowed to increase the number of turns keeping the radius constant, again I can change the length of the wire. So it will be a straight line. Your m will be directly proportional to L. Again, if wire is allowed to be made longer. Similarly, it is also proportional to the current. You can see that right over here. If more current passes, obviously you will see more magnetic moment will come. Magnetic moment is proportional to the current in it. This is true as long as I'm allowed to change the length of the wire. But see how things will change if I am keeping the length constant. So that is why I say it's very important you see what is constant and what is not constant. Magnetic moment is Ni into A. A is basically pi r square. If, for example, length of the wire which is making those coils is kept constant, then the length of the wire is nothing but the circumference 2 pi r into the number of turns. That is a constant, which is basically the length of the wire. So therefore r will be equal to length of the wire, which is that constant, by 2 pi n. So if you observe carefully what will happen over here, magnetic moment will be n I. Instead of r, I can put it as L square by 2 pi n. So this will become I pi L square, sorry, this is 2 square pi square n square. Is that right? 2 square pi square n square. So I think one pi will go from the top. It will be current. One n will also go from the top. I L square by 2 pi n. That is what I will get the magnetic moment as. So it is inversely proportional to n. So it is inversely proportional to n. So magnetic moment will go like this. Magnetic moment will be inversely proportional to the number of turns. Will be inversely proportional to the number of turns. Very, very different analysis. In the previous one, it was directly proportional to n. Here it is inversely proportional to n. Similarly, you can get it in terms of radius also. You can get it in terms of radius also. From here, you can also see, instead of going from here to here, we can also write it as number of turns will be length by 2 pi r. Length by 2 pi r. So if I substitute that over here, what do I get? Magnetic moment is equal to, instead of n, I will put it as L by 2 pi r. Here I'll have I pi r square. So it will become magnetic moment as r will cancel, pi will cancel. So it will become L I r divided by 2. That's it, pi gone, r gone. So magnetic moment is directly proportional to r. So it will be like this. Magnetic moment is directly proportional to r. This is true if the length of the wire is kept constant. So you can see, if it is allowed to make longer, the answers are completely different. If the wire's length is constant, then the answer is completely different. So things can change like this. So that is why you should not only know the formulas, okay, apart from the graphs. Only then you can draw the graphs. Otherwise, gone. Yeah. Got it, guys? Understood? Clearo? Very nice. All right. Cool. Then we can go to AC. Other than that, there is nothing else in inductance and all these things. We can also do electromagnetic waves if you want. Electromagnetic waves, it's very simple. The graphs, it is like you have electric field and magnetic field which are perpendicular to each other. E cross B, right? E cross B is C. Okay. So I'll have to draw it like this. You will see that both of them are basically perpendicular to each other. One is magnetic field and the other one is electric field, and this is the direction of the velocity of the light. These both are perpendicular. Everywhere they are perpendicular. No matter which field you take, whatever you do, they are always going to be perpendicular to each other. And the formulas go like this. We'll have B cross B E by B is speed of light. E cross B is parallel to the velocity of the light. These are two major equations which you should know when you look at this graph. And electric field, magnetic field and velocity of light are mutually perpendicular to each other. And E cross B, electric field cross magnetic field, is going to give you the direction of the velocity of the light. This is another very, very important equation. Obviously, C is equal to F lambda, which is also equal to omega by K, which is also equal to 1 by root permeability into permittivity. All these formulas are still valid. Okay, for the velocity of light. It's 4, sir. Okay. Is it? Oh, yes. Thank you. I put 2 by mistake. Yes, this should have been 4. Thank you. Yes, thank you, Krishna. Very good observation, very keen observation. Very smart students we have. Yes. Yes, Yashasvi, very good. Yes, you noticed it. Okay. Okay. Shankar, I have done both ray and wave optics. I'll just show it to you right over here. Just search for ray on our channel. You will find ray optics part 1 and part 2. Okay, it's done already over here. Okay, ray optics part 1 and part 2 both are there. You can just check it out on our channel. And if you want wave optics also, that is also done. Just try to search wave. You will see over here. Waves on a string and sound. Okay, and wave optics. Both are done. Both are done. Okay, with NCRT and PYQs, with NCRT and PYQs. Both things are done. 3.5 hours class, 3 hours class, everything has been taught in this. Okay, so it's there right on the Vedantu NEET English channel. Is that okay? Fine. Shankar, Shiva Shankara, nice name you got. Okay, okay. I would say right now, instead of the block video, I would suggest you to watch that, because I feel I can put in my efforts in other content like extra problem solving rather than teaching the same theory again. Okay, I know I can do it again in one shot. I can probably do it in 4 hours, but I feel there is a lot of content which I can give in problems wise, in revision wise, in other one shots and predictor papers and sure shot questions wise, and the last minute exam, how to do a lot of other things during the last moment in the exam. So I feel I can deliver better content over there at this point of time, because time is very limited. We just have 10 days. That's the problem. Okay. Yeah. Cool. Then what else do we have? Let's go ahead. Magnetic moment, this is done. Electromagnetic waves, this is done. Okay. AC generation. AC generation. AC generation. The equation will be like this. When you generate a alternating current, the graph is like this, sine graph. So the EMF generated is magnetic field into area into angular velocity into number of turns into sine of angular frequency into time. This is the graph, and this whole thing I can just call it as E naught. I can just call it as E naught. So this E naught is the amplitude of that particular alternating voltage. This is voltage versus time graph. This is also called as the peak voltage. And that voltage which generates the same energy or the power as that of this varying voltage, that is basically called as RMS voltage, and that RMS voltage is the maximum voltage divided by √2 for your sinusoidal graph, for your sine kind of AC wave. So what is this value? When you take a coil inside the magnetic field rotated, alternating current is generated. That is the equation for this particular thing. Yeah, voltage versus current graphs is the next thing. So say for example, this is your time, and let's say I show the current like this. This is the current graph. This is the current graph, and let's say I show the voltage graph maybe like this over here. Slightly difficult to draw. Something like this. This is voltage graph. You can see current and voltage are not in sync. they are having some kind of a phase difference, and that is also shown in the phasor diagram. That is also shown in the phasor diagram. So this is your phasor diagram. Here you can see the voltage is already reaching the maximum value before the current does. So voltage is ahead of the current. Voltage is ahead of the current. So usually it is shown like this. If this value is V0, then the length of this phasor is also V0. It is ahead of the current. So let's say the maximum value of current we get is I0. Then the current phasor is shown of that length only. And the angle between them, is the delta phi or phi, whatever you want to call it. That is your phase difference between voltage and current. That is your phase difference between your voltage and current. Very good. Excellent. Yeah. Is that okay? Very nice. Now let's see other things. Let's see other things related to AC. There are two important phasor diagrams which you should know. On the horizontal line, you show always the current. And then you show the voltages in LCR series circuit in the following manner. Always the voltage across the resistor is in phase with the current. So I can always say VR is current into resistance directly. Then the voltage across capacitor and inductor. For inductor, always show it on the top. So voltage across the inductor is current into basically XL. XL is inductive reactance, which is omega L. The voltage across the capacitor, I can probably show it like this, which is VC, which is current into resistance of the capacitor, which is XC, capacitive reactance, which is given by 1 by omega C. And the resultant of all these three vectors, this, and this, will look something like this. Remember, this height will be VL minus VC, whichever is more, whichever is less. Accordingly, the graph will shift on the top or below. And this will be the total voltage. This will be the total voltage. And this angle will be the phase difference. This angle will be the phase difference. A similar graph we can also show over here for resistance. Again, you show current on the horizontal line. You show the resistance over here. You show the resistance over here. You show the inductive reactance over here, which is basically XL. You show the capacitive reactance over here. Take the resultant of all of them. Take the resultant of all of them like this. This will be XL minus XC. If this is more, this is less. If that was more, this is less. The graph would have come down. And this would be the phase difference. The hypotenuse is Z, which is impedance. And you can also write V is equal to IZ. V is equal to IZ over here. Z is the total impedance of the circuit. Very, very important again. Okay. So these two triangles you should definitely know. Okay. Another important graph is the resonance curve, or how LCR circuits react to different frequencies. This is the omega of your source voltage versus the current in the LCR circuit. Current in your LCR circuit. This graph looks something like this. This graph looks something like this. Actually, it goes here and goes like this. Here you will get maximum current. This maximum current happens when omega of the source is equal to the omega natural frequency, which is 1 by root of LC. And this maximum current is total voltage by resistance, and at this point you say resonance occurs. At this point you say resonance occurs. Basically XL is XC and the total impedance is purely resistance. Phi, phase difference is 0. Power factor, the power factor is 1. This is the speciality of resonance. Very, very important. At this particular point, omega is 0. So this is basically a DC circuit. This is a DC circuit because there is no change in the frequency. So this is purely a DC circuit. Keep that in mind. Yeah, correct. Okay guys, everyone. Actually, this graph should not end over here for a DC. It should, because when current is constant, capacitor will block it technically. So basically the graph should go to 0 over here. Yeah. So as you come more and more over here, you are coming towards more and more DC circuit. So DC, because omega is not there, it will completely block out the current, right? So this is there in your alternating current. Apart from this, you don't have much over there. One more thing probably which you can look at in alternating current is the power triangle which is there, and that looks something like this. You draw a triangle. Right angle triangle with the hypotenuse as voltage into current. That is called as apparent power. This is apparent power. And then the phase angle between voltage and current, you put it over here. So naturally the base of the triangle will become VI cos phi. This is the actual power. This is the actual power which is consumed. Cos phi is the power factor, remember that. And this one, which is VI's sine component, VI sine phi, is called as the reactive power. Reactive power. Reactive power. This total triangle is called as the power triangle. Power triangle. Very, very important. Is that okay, my dear warriors? Yep. Awesomeness. Right. Very good. Great. Okay. Just that I remembered few things in ray optics. Only 1 or 2 graphs which are there. Yeah. So we'll do that also. 1 or 2 graphs which we can get in ray optics, and that is very, very simple actually. That is related to your, minimum deviation. Let's just do it probably here. Just remembered. So for minimum deviation, delta versus angle of deviation, this is in prisms. That is the only graph which is there. Suddenly I remembered. Okay, so the graph looks something like this. This is your point of minimum deviation, where incident angle is equal to the emergent angle. Also the internal angles are equal, and at this particular location you can write refractive index is sine of a plus minimum delta whole thing by 2 upon sine of a by 2. The graph is not completely symmetric, but for small angles it is almost symmetric. Okay, for small angles here and there it is okay, but for large angles it is not completely symmetric. That is something which you should know. This is for a normal prism, but if you take a thin prism, if you take, let's say, a thin prism, then the graph is slightly different. I mean, it is same, but just that instead of being curved so much, the graph is hardly curved. It is like this. Yes, you will get delta minimum over here. Delta minimum over here when incident angle is emergent angle, but for other angles also it is almost the same. So delta is equal to delta minimum, and that delta comes out to be as angle of prism into refractive index -1. So this is only true for thin prisms because delta is almost the same for most of the incident angles. That is something which you must know. One more thing again in optics which you can also remember is on the screen, if you look at the y coordinate, if you go on the screen and plot the graph of y coordinate versus intensity, this is the center of the screen. This is on the screen. You take, on the screen, you take multiple locations. How will that intensity graph look like? For Young's double slit experiment, it looks something like this. Let's say this is in Young's double slit experiment. Young's double slit experiment. This is how the intensity graph looks like. But in case of single slit experiment, the graph is very different and little bit similarity is there. Single slit experiment for diffraction, for basically diffraction. If let's say the maximum intensity occurs over here and minimum intensity occurs over here, the next maximum intensity is not so high. It is like this. In fact, I can show it of a different width only. If it is like this, it's like this, it's like this, it's like this, it's like this, like this, and like this. Here also, like this, like this, like this, this. This is for single slit. The intensity keeps on reducing. That is the major difference in the intensity graphs. So when you go to the next maxima, the intensity is less. After two maximas only, the intensity dies out very, very rapidly. So negligible intensity is there. Yep, correct. In refraction, there is no such other graph which I remember. Yeah, mainly these things only. Yeah, cool. So let's go to the next thing, and that is modern physics. Very few graphs are there. I know Diksha ma'am will be waiting. I'll just finish off within the next few minutes. So in photons, what all graphs are there? I'll tell you. Say for example, energy of the photon is hf, which is also hc by lambda. So if energy versus frequency graph is asked, it will be like this. Energy will be directly proportional to the frequency. But if energy versus wavelength graph is asked, it will be like this, because energy is inversely proportional to the wavelength. What about energy with respect to momentum? Well, think about it. Momentum is nothing but h by lambda. Momentum is nothing but h by lambda. So energy, right, because lambda is h by p, momentum is h by lambda. So energy is nothing but P into C. P into C. That's what you will notice, right? You will see it is P into C. So basically it is directly proportional to the momentum. So energy is directly proportional to the momentum of the photons. All of this was for photons only. This was purely for photons only. Then, if you talk about wave particle duality, if you talk about dual nature of particles, right? Then lambda, the de Broglie wavelength is h by p, which is 1 by root of 2m into kinetic energy, which is 1 by root of 2 times m into charge into voltage difference. So if I were to draw the graph of wavelength versus momentum, that graph will be like this. It is inversely proportional. It is definitely a hyperbola. It is definitely a hyperbola. But if I were to draw it versus energy or voltage difference, then it is inversely proportional to root of kinetic energy and all of that. So it will be a curved line. It will be a curved line, but not a hyperbola. It will be some curve. It will be some curve. So lambda is inversely proportional to voltage difference, or it is inversely proportional to root of kinetic energy. If kinetic energy decreases, lambda decreases. So it is a curve like this, but not a hyperbola. Is that okay, everyone? Keep this in mind. Right, very good. Then you have graphs in photoelectric effect also. Like for example, how does the current change with intensity? How does the current change with intensity? How does the current change with intensity for a photoelectric setup? For photoelectric setup. That graph is simply put a straight line. Current is directly proportional to the intensity. This is only true if the frequency of the photon is more than the threshold frequency, or the wavelength is less than the threshold wavelength. Only then photoelectric effect can occur, or else there will be no current no matter how large the intensity is. This is one important graph. Next important graph in photoelectric effect, I think, yeah, I can put over here only, no problems. You have stopping voltage over here. Wait, let's see. The original equation was HF is equal to HF naught plus EVS. So moving around, EVS is equal to HF naught minus HF. So VS will be divided by E. So it will be minus H by E into F minus plus HF naught by E. Okay, if I want, I can do one thing. I'll put it frequency over here. Oh, no, it was fine only, I think. EVS. Oh. 1 second, guys. Sorry, my bad. What did I just do? EVS is equal to HF minus HF naught divided by E. So VS will be H by E into F minus H by E into F naught. Okay, no issues now. So this is like Y, this is like M, this is like X, this is like C. It's a straight line equation. So you will notice you will get a straight line equation like this if you draw a graph of your frequency, Y is stopping potential, so Vs, and x-axis is basically your frequency. X-axis is basically your frequency. This graph can't go below 0, so I will just show it with a dotted line because stopping voltage can't be negative. It is, yeah, shown in a dotted line. The slope of this graph is always constant, which is H by E. It is same for all the materials. It is same for every kind of material that exists on Earth. So you can use a different material, the intercept will be different, but the slope will remain the same. But the slope will always remain the same. Yeah. The y-intercept that we talk about over here, the y-intercept that we talk over here is basically minus HF naught by E, which is basically minus work function by E. This depends on the material. This depends on basically your material which you are using. Depends on the material which you are using. Should we study rolling motion? Yes, you should study rolling motion, but little bit. Yes, you should study little bit of rolling motion, not required too much. Yeah, correct. Then there is one more graph. which is your current versus the applied voltage in photoelectric effect, in your photoelectric effect. And that graph looks something like this. This is for some low intensity of light, and this point is your stopping potential for that particular intensity. If I change the intensity of the light, then the stopping potential obviously won't change. The current will increase, that's all. The stopping potential will remain the same for low or high. It is the same thing. Only the currents will increase, because the stopping potential, how can it be affected by intensity of the light? It only depends on the energy of the photon and the work function, nothing else. So this is another important graph. And if you are wondering what is this current called when it reaches some value, this is called as saturation current. This is the maximum current which can be flowing in a photoelectric setup. This is also called as the saturation current, maximum current which can flow in that particular thing. Correct. Very good. Very nice. Okay. Then the next thing which you need to know is the different proportionalities in case of Bohr's model. In Bohr's model of atom, that's all was there in wave particle duality, photons and photoelectric effect. In Bohr's model, few things like radius of the Bohr's model, my dear warriors, is directly proportional to n square by z. So if you draw the graph of radius with respect to n, it will be basically like this. Radius is proportional to n square. Correct? Similarly, velocity is proportional to z by n. So it will be inversely proportional. Velocity is inversely proportional to n. And lastly, energy is proportional to z square by n square. So that is why it will be basically like this. So energy is, and by the way, energy is negative, so it has to be below. Remember, energy is negative, so the graph of energy will be over here. So energy is inversely proportional to n square. That is how these graphs will look like. Yeah, that is how these graphs will look like for different n values. Very, very again important. Yeah. Oh, Diksha ma'am's class might change. Okay, power has not yet come. Okay, I will pray that the power comes only after my class ends. Diksha ma'am will kill me if she listens to this. Okay. Okay. So the PDF of this lecture, RSBK, female team, Manshur, oh my god, what names. You will get it in the Telegram channel, and in the description box or in the comment section, it will be updated after some time. Okay. So keep a track of Telegram channel, link is there below, and also in the description box, both the things. Then what else? Energy levels. Okay, for energy levels, I think we'll take this slide only. Okay, this is your hydrogen energy level diagram using Bohr's model or any atom's energy level diagram for different shells, correct, for different shells. Yeah, so basically the lowest energy level, n is equal to 1, is obviously called as the ground state, is obviously called as the ground state. This is called as a ground state. This one is the first excited state. This one is your second excited state. Remember, if n is 4, it will be third excited state. So if it is n, then it will be n minus 1th excited state. And this is when you completely are free. You are free from the nucleus. It's gone, right? And this will have 0 electron volt energy. So this is your hydrogen energy diagram for different levels, right? Hydrogen energy diagram for different levels. And for n is equal to 1, for hydrogen, the energy level, the energy is minus 13.6 electron volt. Minus 13.6 electron volt. I would also suggest that you remember few values for at least n is equal to 2 and all of that. Like for n is equal to 2, it is minus 3.4 electron volt. It will save you a little bit of time. That's it. And here it is like minus 1.51 electron volt, right? And here it is, what is it? Minus, how much is it? Minus 0.85, I think. Yeah, minus 0.85 electron volt and so on and so forth. At least 3-4 values, if you remember, it will be very easy for you to solve the problem. Also remember the energy required to go directly from here to here. The energy required, wow, 1 second. The energy required to go directly from here to here. This one is called as the ionization energy. And usually the formula for that is 13.6 Z square by 1 square. If you are going it from first state, yeah, that is the formula, right? Keep that in mind. Depending on where the first electron is, if it is here, then this will be the ionization energy. Z can be different if it is not a hydrogen atom. Okay, keep that in mind. Other things which you should remember is Lyman, Balmer, Paschen and all of that. I think you guys are pretty much aware of it. For example, long, small wavelength, like these ones. Right. What are these lines called? Versus these lines. 1 second. Small energy, large wavelength. Okay. Okay, this is basically your Lyman series. This is basically your Balmer series. This is basically your Paschen series. Why did I show them in these colors? Because the way in which it is. Yeah, like for example, Lyman series is in the ultraviolet range, Balmer is in the visible range closely, and Paschen is in the infrared range. Okay, how do I know it like this? Because you can see the energy difference is very huge. If energy difference is huge, the energy of the photon is also huge. If the energy of the photon is huge, frequency is large, like for ultraviolet. Then you go to lower frequency and even lower frequency. So from ultraviolet, you are going to visible to infrared. That is the reason for that. Okay, ultraviolet to visible, white light is visible, right, to infrared. Understood why I have shown it in that color? Got it? Yeah, very good, very good. So all these diagrams will be very, very helpful for all of you. Yes, awesome, awesome. Then another important graph. Okay, yeah, there is one more thing which you should know. If you take any any electron's orbit and you show that electron's de Broglie wavelength on that orbit, so if you are basically considering any one wavelength over here, this is basically your de Broglie wavelength. This is de Broglie wavelength of the electron in Bohr's orbit. In Bohr's orbit. Then n times of that de Broglie wavelength, n. If you multiply it n times, what you get is the circumference of the orbit, which means it is 2 pi radius of the nth orbit. This is a very, very important graph and visualization which you must know. Keep this in mind. Then in atoms, nothing else is there. You have nucleus. In nucleus, the size of the nucleus related questions. Size of nucleus related questions, guys. Like for example, radius of the nucleus is R0 a raised to 1 by 3. Density of the nucleus is basically a constant. Density of the nucleus is basically a constant. So density graph will be always a straight line if this horizontal line represents atomic mass number and this was your density. But instead of density, if it was radius versus atomic mass number, a raised to 1 by 3. A raised to 1 by 3. So a raised to 1 by 3 means it will probably go like this. This is how the graph will be. So R is directly proportional to cube root of A. Remember, square root of A was also like this. So cube root, fourth root, these graphs are like this. This is how the graph looks like. Is that okay, everyone? Very good. Then you have okay, let me just create a duplicate of this and keep it over here. The binding energy per nucleon graph. The binding energy per nucleon graph. How will the binding energy per nucleon graph look like? So on the y-axis, you have binding energy per nucleon. Binding energy per nucleon versus your atomic number. This graph basically goes up like this and then it comes down over here. The maximum value is for nothing but iron. Okay, these are heavy metals, these are low atomic number metals. These ones undergo fusion to become stable. They undergo fusion to become stable, whereas these ones are radioactive materials. They can disintegrate and they undergo fission to become very, very stable. This binding energy per nucleon is directly proportional to the stability of the nucleus. This is directly proportional to the stability of nucleus. If it is more, then the binding energy per nucleon is more, then stability is also more. Keep this in mind. Okay, clearo? Very good, very good. Then any other graph that we have? Yes, we have Yeah, that's all that is there in nucleus. Nothing else is there. In semiconductors, the only graph that is very, very, very important is the current versus voltage graph. The current versus the voltage graph for a PN junction diode. And it is different for positive, that is forward voltage, and reverse voltage. For forward voltage, it is like this, and then it suddenly kicks up. Here you have something called as the knee voltage, after which the barrier is overcome and sudden surge of current is there. So this is the knee voltage, and here this side is basically forward bias. Here voltage and current are obviously not proportional, you can see that. In the reverse bias, you will see that there is a small current which is there. You can see that current is called as a leakage current, and this goes on for a long time till a breakdown occurs, and suddenly the graph turns like this, and you can see that the voltage is going to be constant, which is called as the breakdown voltage, and Zener diodes are operated in this range. Photodiodes are operated in this range. LEDs are operated in this range. So if I plot the applications, LEDs will operate in this range. This is an example. Photodiodes. So if you want, I'll just put symbols over here. That will be better. So LED operation happens over here. Light emitting diodes. Light is coming out of it. Photodiodes. Light falls on it. Photodiodes are operated in the reverse bias leakage current region, and Zener diode is operated in this region. So the symbol of Zener diode is over here. So always remember this. Yeah, very, very important graph again. Correct. Then which other graph is there? Yeah, I think we have rectification graphs, maybe rectification graphs. So if I think we can put over here. One second. Okay, this is time, this is also time, this is also time. Let's say the first graph represents input voltage. The second graph represents half wave rectification. And the third graph represents full wave rectification. Rectification is a process where AC voltage is converted into DC voltage. So if our AC voltage was, for example, like this, in half wave rectification, only half of the wave is rectified. So it will be like this, nothing at all, like this, nothing at all, like this, nothing at all. Half the wave gets wasted. In full wave, the entire wave is rectified, so it becomes unidirectional. So whatever is there down, it comes on the top. Whatever is there down, it comes on the top. So that is the graph of a full wave rectification. That is how it looks. Now this is before filtering. By the way, remember the diagrams of half wave rectifier. For half wave rectifier, the diagram looks something like this. You have this AC, and you have just one diode over here. That's it. You have a resistor, and you are measuring the voltage. Input is over here. This was your input. This is your input. That is how the diagram looks like. For full wave rectifier, the diagram looks something like this. You generally use a center tap transformer, something like this, a diode over here, and output going like this, and then a diode over here, and it going like this. That's how roughly the center tap full wave rectification processes look like. If you use a capacitor after this, then what happens is, with a capacitor, then this graph, bumpy graph, becomes like very smooth. So very, very smooth. So I can plot another graph over here. This is also with time. But if you use a capacitor, the graph looks somewhat like this. It's almost a constant. This is the process of filtering and smoothing out using capacitor. So here there is a ripple effect, ripples in water, ripples on water. So there is a ripple effect which is removed using a capacitor. That's all. That's what you should know. Correct. How much weightage can you expect in these graphs? You open any NEET paper and check out for yourself. Just check past 5 years. How many questions do come from graphs? There are many questions. Okay, there will be many questions. This is proportional to this, that is proportional to this. This increases 5 times, that increases this times. This is increased 10 times. How much will this change? How many times? Graph is there, question on that. Or question is given, which of the following graphs will match? Or temperature pressure graph is given, which corresponding graph is there? Graph is given, find the area. Graph is there, find the slope. Obviously, you will have more than 4 to 5 questions. So easily 20 marks you can expect. Easily 20 marks. Easily, I'm saying. Proportionality based questions, ratio based questions, graph based questions, choosing the graph, converting the graph, graph interpretation. Obviously 5 questions bare minimum. Right? Yeah. Great. So these were some of the graphs. I don't think any other graph is remaining. Just remind me if anything else we have left out by mistake or by chance. I don't think so. But yeah, I think most of the graphs are done. Cool. So guys, remember that your final last few mock test series, yeah, you need to give them. The link is there in the description box below. Make sure you are making the best use of it. If you are wondering where it is, I'll just show it to you as you are particularly watching this video. Yeah, where did it go? Where is our graph? Yeah, this one. Yes. So right over here. Okay, if you see in the description box, All India mock test series. Link is there right over here. Telegram link is also there here, where you'll be getting today's PDF. So just click on this particular link. There you go. You will get the All India mock test series link. It is completely free of cost. Last few days are there. Make the best use of it. You will get ranking plus report cards. Okay. So these are the 2 most important tests, because these are master tests, and you can see some old tests which you have not given live. At least you can give it recorded and get to know where you stand. Okay. So those are your mock tests. And I want everybody who watched this video till the end to say NEET 2024 will be mine in the comment section. Because if you are religiously following all the classes, if you are sincere in your studies, why won't NEET 2024 be yours? And even if you feel that you have cheated all this while, even if you feel that no sir, I have not done much all this while, and at this point of time, how much can I really improve? Obviously, every day that you study more, you will be adding 10, 20, 30, 40 marks. And even if you study for the next 10 days sincerely, those 10, 20, 30 marks into 10 might translate into at least 100 marks, 200 marks, even 300 marks. So it's up to you how you use these lectures. Every day you are improving. Don't give up. Even till the last day, you might be adding 10 marks. You might be adding 20 marks, and that 10, 20 marks will make a huge difference. So keep working hard and keep saying to yourself, NEET 2024 is my NEET. It is my last NEET. This is meant for me. I am going to conquer it. And that is what the attitude of every NEET aspirant should be. Don't waste your time watching stupid videos. Will NEET be difficult or not? Some people, I don't know why they make such videos at this point of time and scare students. Don't watch such videos. Many people will make it. Okay, some people will also try to watch some videos. Sir, if I take a drop right now, how will the next NEET exam? Arey, my dear student, you don't even know how this NEET exam will be. Maybe you might just pass. Maybe you might just get a decent college. Who knows? So don't waste your time how NEET exam will be, whether this will come, that will come. We will put our 100%. Okay, and our attitude is very simple. No matter how the question paper is, we will make it easy. We will feel that it is easy. We will be able to solve everything. That should be our attitude and mindset. Not that, oh, the paper is easy, okay, we can chill. Oh, the paper is difficult, oh my God, gone. Nothing like that. We have to have complete faith in yourself. That's why NEET 2024 will be yours. Remember that. Okay. So thank you very much, everyone. Glad that you attended till the end, and do not forget to like the video if you have not yet done that, and subscribe to the channel. That's very, very important. Bye bye. Take care. This is Captain Shreyas signing off. Hasta la vista.